Hello.
Hello, sir.
Yeah.
So we are live on the YouTube as well.
Okay. Now, can you get all these other speakers on the screen? They have to.
Yes, sir.
Good morning, madam. Good morning.
So I'm removing myself from the screen. So you take it ahead from now.
Okay. 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 So, good morning, everybody. And today is going to be a very unique day in the history of Bangur Nagar Art, Science, Commerce College, Dandeli. This is the Dandeli Education Society's one of the premier institutions giving the education to the economically poor section of the society since last 4 decades, quality education at the affordable cost. And we have been joined in this webinar with another equally very powerful and philanthropic educational society, the KLE Society, which is very strong and prominent educational wing in this northern part of the Karnataka state. They are also involved in giving education from lower secondary level to the PG level, engineering education, medical education in a very big way. KLE Society is a very powerful educational wing in this part. The KLE Technological University, BBB campus Hubli is also part of this webinar. They are also the co-sponsors, co-host of this. And the accuracy unit of Dandeli Bangur Nagar Degree College, the CFAR Solutions, a consortium has been constituted of the experts who are well versed in the field of research, synthesis, academics, and they want to give some academic and research solutions to the student community to make them uh, employable, they to make them equipped with the needed knowledge required for the industry. So, with all this in mind, we have taken up this initiative of introducing a very emerging and very strong technology of flow chemistry, which is most of our university and also the college students are unaware of this flow chemistry aspects. It's a new technology. Hello, are you? Am I audible to you? Am I audible? Hello, 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 hello.
So please continue. You are audible.
Yeah, okay. Okay. So, this flow chemistry, which is an emerging technology, which is making lot of inroads into the field of medicinal chemistry, drug discovery. So we want to give some kind of fundamentals in this flow chemistry to our students who are at UG, PG, as well as doing some research. So this webinar is mainly introduced to our students to the new emerging technology and the faculty members who are working in colleges as well as universities. And with NEP, the new education policy, which is unveiling very shortly in the country and Karnataka state in particular, skill-based education will be the integral part of the curriculum. So faculty have to equip themselves with newer and promising fields so that we can make our UG, PG students well equipped to suit the industrial needs. An exposure to our UG, PG, and research students to this technology-driven field of flow chemistry will give them an added advantage in their performance, enhance the employability and entrepreneurial skills. Under this backdrop, this webinar is organized and the discussion on various aspects of flow chemistry will be dealt by the eminent speakers from far and wide places of the globe. Basic and applications with case studies will be dealt in this webinar. All the speakers have expressed their ardent desire to help the student in their academic career wholeheartedly. We are truly fortunate to have a galaxy of speakers belonging to premier academic institutions and world-class research organizations to be the part of this webinar. We must express our sincere gratitude to Professor Anil Kumar, Sir, IIT Bombay, and Dr. Ashwardhan Malparni, Devung Bio Incorporation, South Korea, who is also the alumni of our college, from bringing all these excellent luminaries in their field under one platform for the better cause of industry academia synergy. So, on behalf of all the organizers, on behalf of our management, on behalf of all the host organizations, I am extending a very warm welcome to all these eminent speakers who are going to give the talk on their chosen topics. A warm welcome to Dr. Shobha Sharma, the principal of Bangur Nagar Degree College, Dandeli, Dr. Prakash Vasmani, coordinator, IQAC, Professor T.M. Amin Bhabi, who is the Dean of School of Advanced Sciences, KLE Tech University, PUB campus, Hubli. Speakers, Dr. Karuna Veermani from Dr. Reddy's Institute of Technology, and who is heading the Flow Chemistry Technology Hub at Hyderabad. Dr. Vidyacharan, who is residing in US, and he is joining as the first speaker. And Dr. Karuna Veermani is going to give the keynote address. Dr. Nagaraj Nayak from IIT Bombay, Dr. Arun Nikam from Pune, and Dr. Shobha Yan from Metlar Instruments, those who are involved in making the instruments of required or used in this flow chemistry, and Dr. our own alumni, Dr. Ashwardhan Malpani. So with this, I welcome you all once again, and I wholeheartedly thank all of you for taking this initiative to help the academic cause and to help the student community to gain little bit of knowledge in this field. And I request our principal, Dr. Shobha Sharma, to declare this webinar open by saying hello and saying few words to these speakers and other people. Dr. Shobha Sharma. Okay, I will inform just a minute. Just a minute. Abhishek, you let in our Dr. Shobha Sharma principal on this Melon or Melon stream. Shobha Sharma. She said she's not been allowed, not allowing something like that. She told. Yeah, I will inform her. Okay, okay. There are some technical issues in live. So I once again extend a very warm welcome to all the speakers and the other participants who have joined through various social platforms, social media platforms. I welcome once again, and I request Dr. Karuna Veermani to give her keynote address. And before that, I would like to inform the participants, those who have joined through various streams, that each session we will be giving the introduction of the speakers session by session, and there will be a chat box. If you have any questions, you can type it and put it into the chat box. We will take up the questions session by session, because the speakers may not be there available throughout the webinar. They may be going out of the webinar once their turn is over. So we will take up the questions as and when the sessions, each session is over. And I request the participants to write the questions when they have any questions regarding that particular presentation during the session. And before I request Dr. Karuna Veeramani to give her keynote address, I will give a brief introduction about Dr. Karuna Veeramani. Karuna Veeramani is a senior research scientist, Flow Chemistry Technology Hub, Dr. Reddy's Institute of Technology, Hyderabad. Dr. Karuna Veeramani did her bachelor's in pharmaceutical science from Bharati Vidyapeeth College of Pharmacy in Navi Mumbai. First, she pursued her postgraduate studies, MS from Naipur, Hyderabad. Subsequently, she completed her PhD in process intensification for the synthesis and application of heterogeneous catalysts through continuous flow chemistry under the guidance of Professor Anil Kumar, Department of Chemistry, IIT Bombay, and presently associated as a senior research scientist with Flow Chemistry Technology Hub and Center for Process Research and Innovation, Dr. Reddy's Institute of Technology, Hyderabad. Her research interests mainly include flow chemical aspects of nanotechnology and chemistry, how flow has emerged over the recent years as an efficient synthetic tool, and why flow, both in theory and practical forms, essential in developing sustainable future. With this brief introduction, I welcome Dr. Karuna Veeramani and request her to give the keynote address of this webinar. Thank you.
Thank you very much, sir. Hello, am I audible? Hello, am I audible?
You are
Hello,
audible, madam.
and the slides are visible, sir?
No, not yet. Now they are visible.
Okay, thank you very much.
Thank you.
Okay. Firstly, I want to thank Dr. Medwade for his very kind introduction to me. It's a really great honor to present a keynote address, but along with that comes a very huge responsibility of explaining such a important sort of chemistry to the young minds that will be listening in this webinar. So it gives me immense pleasure to start. So, as he said, I'm Dr. Karuna Veeramani, a senior research scientist at DRILS, Hyderabad. I have entitled my topic as Continuous Flow Chemistry, a contemporary space for conventional synthesis. Now, firstly, I want to justify as to why this title would be a very good way of starting the talk or the webinar on flow. Firstly, in order for us to understand as to what is the difference between basically batch and flow chemistries, let's consider these two diagrams over here. This is a typical batch reaction where you have reagents A and B getting into a round bottom flask to react to give the product P. On the other hand, if we do the very same reaction through flow, you simply take a tube like this, insert in A and B through different tubes into a single tube, which inside which the reaction happens, and then you get the product P at the other end of the tube. So this is a very simple representation of the difference between a batch and a flow reactor. In order to understand these points in a little more better way, these graphs will help us to do so. As you can see over here, this is a batch reactor and this is a flow reactor. So as we can see, the concentration of A and B, as in the reactants, decrease with time as the reaction proceeds, and the concentration of P, which is the product, increases with time as the reaction proceeds in a typical batch reactor. So, on the contrary, when we see, if we take a simple flow reactor, at every point of time, there will be A and B mixing together and pushing the product P forward in order to give you the final yield. So, as we can see over here, the basically the time which is there in a batch reactor could be equated to the length in a flow reactor. Or in other words, if we see, for a very simple example, if we are supposed to take out a sample point at the fifth minute of a batch reaction, the point at the 4.5th minute and the 5.5th minute will be very different as compared to the fifth minute in a batch reactor. Or in other way, a batch reaction is more time dependent. On the other hand, if you take a flow reactor, at the very same fifth minute time point, you will get only one particular result at every time that you sample at that same point. In other words, to cut the long story short, the time in a batch reaction is equal to the length in a flow reaction. This is what is the most basic advantage and a very important advantage of continuous flow over batch chemistries. Going ahead, firstly, I want to also give a brief idea on why are flow chemistry publications increasing so much over the time. Why is flow that important? We can see that there are so many journals that have come up over time. All of them have cover page articles speaking about flow chemistry and how it's doing wonders in the world today. And this is a particular statement by a very important review journal, which says that it's very hard to pick up any scholarly journal article today where flow chemistry is not present. So this itself gives us a very clear idea of why flow is increasing with time, why the importance of flow is developing so much with time. So this is a very important thing that we need to address, and this is exactly what we'll be seeing today. So in order to understand that, we have to dwell a little into the basics of flow. So firstly, we'll start with what influences the rate of reaction. So basically, the rate of reaction is defined by the Arrhenius equation, which is basically this particular equation, K is equal to A E raised to minus EA upon RT. So over here, we can see that the rate of a reaction is dependent on two factors. One of them is the pre-exponential factor A, and the other one is the activation energy. So when you look into the pre-exponential factor, that is basically the number of successful collisions that can happen per unit time, which is dependent on the concentration of reagents, which is further dependent on the number of collisions. Higher the number of collisions between the molecules, you have better reaction happening. And that is dependent on the concentration of the reagents. The more you have concentration, the better frequency of collisions would be there. At the same time, you also have a very important parameter, which is mixing efficiency. So higher number of collisions can happen if you have a higher mixing efficiency. So these two parameters enable successful collisions that happen per unit time. On the other hand, the activation energy parameter is basically the fraction of molecules that have energy above the activation energy, or basically those molecules which are actively fit for a reaction. So these are also dependent on various factors like the temperature of the reaction, where if you increase the temperature, you have higher molecules above the activation energy. And similarly also on the nature of the catalyst present. So if you have a catalyst, that will actually increase the number of molecules above the activation energy. So basically speaking, these parameters are extremely important for governing the rate of a reaction. So now, there has been a constant battle between speed and control in conventional modes of synthesis. In order to elucidate that, let's see. Now, increased rate of reaction facilitates a higher number of effective collisions, as we initially saw. So that also generates a very large amount of heat. So this uncontrolled heating up of the entire reaction mixture causes the system to contain or sustain an extreme amount of heat at a particular unit of time. Now, this is what is the problem. In typical processes, this heat is not able to be contained by your typical batch reactor. So that causes an explosion, which is a very fast process. So what could be done is, we could help in dissipating this either to the open atmosphere or to a chiller, but that in turn is a very slow process. On the other hand, increased rate of reaction also facilitates large volumes of reagents getting involved. So that actually can cause turbulent or inefficient mixing. So because of that, when you have poor or improper mixing of reagents, the system is incapable of mixing properly and giving a proper reaction. So in that case, what happens is you don't get good reproducibility with time. You don't have the same reproducible or reliable results coming with every batch. On the contrary, this could also be slowed down and made the efficiency of the mixing better, but that again is a slow process. So as we can see over here, these are the two processes which is typically considered or taken up by typical batch industries, like batch processes which industries take up. So that makes the overall process slow as well. So now we'll look into how can flow chemistry help in combating these disadvantages that we just discussed. As we have already seen before, this is a typical tube or a flow reactor in its simplest representation, where A and B react together to give C. So these are the various properties of a tube which gives so many advantages. So by these advantages could be translated into doing flow. So basically speaking, in a flow reactor, you have a very high surface to volume ratio because of the length of the tube and the small volumes inside it per time. So what that does is you have a higher number of effective collisions between the reagents. So you have a better heat and mass transfer. So when you do a reaction in such a tube, the advantages that you get are accurate temperature control and efficient mixing in between the different phases of the reagents. Also, as we saw in the earlier slides, time in a batch reactor could be corresponded to length in a flow reactor. So that makes it more easy for us to work on the various aspects of the reaction, like where the time is visible. So over there, you have accurate time control. Going ahead, when it comes to no secondary growth, so no molecule of the product meets any newly entering reactant molecule, since the flow is completely unidirectional and in forward motion. So because of that, you don't have secondary growth or agglomeration of materials. So this is a very important parameter when it comes to working with nanochemistry. And you have forward flow of reagents every time. So that gives your every molecule same environment or the temperature, pressure and time conditions. So that helps you to work on the reagents in a better way. And that also gives you a very high reproducibility. And finally, you have the continuous nature that is there, which is basically helping you to give an on-demand synthesis or a high throughput or the yield per unit time. And you also don't have a head space or the above space that is there after you have filled in the reagents into your flask to be compared in a very simple way. So there is no place for the reaction system to take in moisture or air. So that also helps you to do gas, liquid or very sensitive reactions in a very easy way. And it's basically an automated or a non-intervened system, so that makes it very easy to explore hazardous chemistries because it doesn't allow the personnel to come in direct contact with your materials. And finally, there are no moving parts like a stirrer or various other parts of the reactors, which we typically see in a conventional chemistry lab. So because of that, you have easy tube to tube optimization. So that gives you a better reaction redesigning when it comes to extrapolating that into the industry. So that, basically speaking, it gives us an enhanced scalability. So we have now seen what are the various advantages that are possible when you do flow chemistry. So going ahead, how can flow chemistry solve the speed versus control challenge that we had just discussed a couple of slides ago? So using flow, you could explore high temperatures, which is given by the Clausius-Clapeyron equation, which says that higher temperatures can be achieved in a tube by application of appropriate pressure. So if you need very high temperature, you just need to give appropriate pressure to the reaction so that the entire reaction could be explored to a higher temperature range than what the individual boiling points of the reagents can tolerate. Also, you can explore ultra-fast temperatures, where the Arrhenius equation again comes into play over here, which says that for every 10-degree rise in the temperature, the reaction rate gets doubled. So as you can see over here, if a reaction takes 8 hours to complete in an 80 °C module, it can actually get over within merely 2 minutes at a 160 °C temperature. So that is a very good extrapolation of how ultra-fast temperatures could be looked into when we are looking at various reactions. And also you have a controlled mixing efficiency because the diffusion time is lesser for a tube than a conventional flask. So you have better mixing that happens, which finally enables your reaction to happen faster as well. So the final note is process control plus reproducibility. Both of them will give us a very new chemistry space for identifying various new problems and trying to solve them through different ways. So this is exactly what flow chemistry does. So now I have like completed giving the technical aspects of a basic flow reaction. So now we can look into what is the anatomy of a flow reactor or what are the different parts of a flow reactor. So as we saw before, A and B mixed together in a tube to give P. So this could be broken down into different parts where you have A and B getting pumped in through a fluid and reagent delivery system, which we typically call as a pump. That gets mixed at a particular point. From there, it gets reacted. And there you could also add a quench line if your reaction demands so. Finally, you have a pressure regulation that is happening. Finally, giving you the collection of the product. So this is how a typical flow reactor or this basic schematic representation could be broken down into its true original components. So we'll discuss very shortly on what are pumps and what is basically the nature of pumps. So basically the pumps could be called as the inlet of a flow system because without this, your flow system is actually non-existent. So the pumps form a very important part of your reaction. So that is basically this particular component in the broken down chart diagram that we saw. So over here, the most basic types of pumps are the syringe pumps, the peristaltic pumps and the piston pumps. Each of them work in a different mechanism. And these are the various commercial models that are available for these particular types of pumps. So as you can see over here in the right hand side of the slide, all these parameters show us what is the sequence or what is the way you should look at when you are addressing a reaction depending upon the flow rates that you require. Flow rate basically means the speed at which your reagent goes inside a reactor, and based upon the type of the reagent delivery, whether it is a solid or a liquid or a gas reagent, and depending upon the pressure tolerance that you need for your overall reaction, all these parameters help you to understand which pumps should be chosen for a reaction. So that is basically about the pumps. And as I said already before, pumps are the most important part of the reaction because these are the tools which actually help you to start with the reaction. So these are the ones which actually give you reagents into your reaction system. So that makes it a very important part of the entire assembly. Going ahead, we'll talk about the mixing unit, which could be translated to the efficiency of a flow system. Because as we have already seen before, efficiency is very directly proportional to the mixing that happens in the reaction. So this is basically about this particular component that we saw in the chart. So there are different types of mixers. This is based on the MOC or the material of construction. There are mixers where you have PEEK as the material of construction. These are the commercial models available. This is the stainless steel reactor, the stainless steel mixer modules that are available. So basically, as this particular diagram very clearly depicts, you simply have the two reagents coming in. They get mixed at a particular small orifice over here, which enables you better mixing because of the small constricted area available. And that further pushes the mixed reagent out. So this is a very simple idea about what are mixers. Even these are extremely important when it comes to a flow setup. Going further, the reactor is the heart of a flow system because that is where the reaction actually proceeds. So that is all about this particular area of the chart. So these are the various reactors that are available. So you have different types of reactors like the coil reactor. This one is the schematic of each of the reactor, and these are the commercial models available. So you have a typical coil reactor, you have a chip reactor. So a coil reactor is basically for multi-phase reactions. A chip reactor could be used typically and exclusively for liquid-liquid reactions. Then you have packed bed reactors where you have heterogeneous catalyst mixing type of solid-liquid reactions or solid gas reactions. You have photochemical reactions, which is basically used for various kinds of important sorts of reactions where you have a lot of light mediated activation to happen. Then you have electrochemical reactions. Then you have spinning disk reactions, which are exclusively for ultra fast mixing. And you also have agitated cell or tube reactions, which basically works on active mixing rather than the passive diffusion, which we have discussed in all the above cases. So here you have basically cells or agitators which react in order to give you the reaction. So regarding these also we will see further in the coming slides. Then the back pressure regulator, which is important for maintaining a flow system. So that is basically this part of the entire assembly. So over here also there are two types of BPRs or back pressure regulators. One of them is the preset one and the other one is a variable one. So based on different mechanisms of action, these give us a proper pressure that is there in the entire system. So that enables us to do two things. One of them is it allows you to keep your entire system in a streamlined fashion. And another, most importantly, is it helps you to keep the boiling points of the individual reagents under its particular range so that you can explore higher temperatures. The earlier Clausius-Clapeyron equation which we saw earlier, so that basically translates with this particular usage. So these are the various types of the components of the various reactions that we just saw. Going ahead, now we look into what are the applications of continuous flow. Continuous flow chemistry is an efficient emerging synthetic tool in various parts of chemistry and scientific research. So in that, we'll first look into API or basically active pharmaceutical ingredients. So as I'm already aware, like as we all are aware, there are a lot of very important molecules which are present in the scientific domain, which is very important for us to look into. So out of them, it's very important for us to look into how to manufacture or scale up lab based processes into efficient industrial process as well. In that scenario, pharmaceutical manufacturing is one of the most important ones that needs this particular attention paid into. So this is an example of ibuprofen, a very common analgesic drug that we use. So it's very important that we understand that such an important molecule could be prepared so easy as in such a telescoped way for giving us this particular reaction. As we can see over here, there are multiple steps involved. It's basically a three-step reaction where you have one particular step one happening here, and that further isolating itself into two, or rather separating based on extraction procedures, and that further going ahead to a step two, and that further consecuting it into step three. So the advantages of this particular process is it is a novel process window based production, and the reaction time merely takes 3 minutes, as we can see over here. The times 1 minute, 1 minute, and 1 minute. So total time of the reaction is 3 minutes, and the average yield per step is more than 80%. And the production rate at a simple 250 microliter reactor range is almost 8 grams per hour. So that actually translates to how important flow chemistry could act in order to look into very important parts of science like the API synthesis. Going ahead, when it comes to controlled handling, this is an example where you have very toxic reagents like the N-butyl lithium. So in these areas, it's very important to look into both parts of safety. Like one of them, when we say about controlled handling, one part of it is control handling towards the personnel, as in we should take care when we are handling that because it's a very toxic reagent. On the other hand, when we say control handling, it's also important to see that these reagents are extremely reactive. So if you allow the reaction to progress for more than a particular amount of time, it can very easily give rise to side products. So that is the reason why handling these reactions in a controlled manner is extremely important. So over here, we could very easily see that the reaction time domains are all in the seconds range. This is 0.82 seconds. This is 6.93 seconds, 0.47 seconds, etc. So we can see that managing reactions as at such low time ranges is practically impossible when it comes to typical batch or conventional methods. So this is exactly what could be very easily addressed when you look into flow. So we could see that it's a space integrated end-to-end process. It's a very good way of safely handling unstable intermediates. And the reaction time, as we have already seen, is in seconds domain. So that does not give us a rapid decomposition of these materials. And thus that helps us to actually progress the reaction in the desired way. So going further, flow chemistry has always been extremely important in the range of materials, and for the last around 3 to 4 decades, flow chemical synthesis of materials has been extremely looked into. So these are the various materials that we can see over here. All of them are controlled morphology materials, as in they have a particular morphology, and that morphology is the reason why they give that particular activity when you translate it further. So this morphology and the surface area that comes out of that morphology are the most important parts of these particular materials. So it's very important for us to retain these particular morphologies in a way that they actually give you that particular efficiency at a later date. So achieving this at batch reactions level is a very difficult thing, or rather we could say that it's again a sort of a competition between control and speed. If you have a very high yield, you don't have a controlled morphology, and vice versa. If you have a controlled morphology, you do not have a high yield. So it's very important to look into how we could manufacture these materials at a high yield as well as this promising morphology along with it. So this is one particular example where they have done a material synthesis where they are like preparing surface functionalized materials. So over here we can see that this is also a multi-step reaction where they are very properly, they are like synthesizing a proper core material. On that they are functionalizing or they are coating the material, and then they are finally producing coated controlled morphology materials. So like this, there are an n number of materials that have been reported in literature which speak about how flow chemistry could be useful for material synthesis as well. So as we have already seen before, it gives us a very high yield as well as a morphological uniformity, which is practically quite difficult to achieve in conventional modes of synthesis. Going ahead, also in the case of polymers, which is a very vast domain in the field of science and technology, even over there, these materials, this way of synthesis has a very important role. We can see that this is a typical polymer synthesis work. So this is a particular polymer, which is basically a combination of different monomers. So you can see that just by increasing the number of reactors that you have over here, you could very easily make as many number of monomer units as you want, depending upon what you require. So that is what we call as a telescoped and a tailored synthesis. You can insert in the monomer you want at whichever point of the reaction you desire by doing this particular way. So this is a very nice example of how you can do tailored synthesis, or synthesis which happens by the way of how you desire it to happen. And you can also see that the conversion in individual steps is more than 90%. So that makes us to understand how flow is a very easy and an efficient way of performing tailored synthesis of polymers in this entire domain. Going further, we'll also look into a little about flow photochemistry. So this is basically a simple representation where you have a flow reactor which is powered by light. So basically it is a traceless chemistry where light mediated reactions can happen. So this is an example of a similar reaction where you have flow coils present. Each of them is illuminated by a light source near it. So that helps us to give you the product through photochemical means, or basically free radical mechanisms. So here a very simple 150 volts metal halide lamp has been used at a reaction time of 30 minutes, and a reactor volume of 37.5 ml could give a throughput of 1.92 grams per hour. There are many other papers which report similar photochemistry as a very emerging tool of using flow in various parts of photochemical synthesis. Similarly, you also have electrochemistry where this is a typical flow electrochemical setup. So over here, if we see, there are various reactions which can happen in this way, like using through electrochemical modes of flow. So I would like to draw your attention to this particular statistics over here. We can see that a typical batch reactor gives you a conversion of around 55% 30 to 30 range at a time scale of 24 hours. On the contrary, on the flow side of it, we can see that more than 40% yield or up to a range of 81% conversion can be possible when we do a reaction through flow at mere time scales of 5 minutes. So that is a very important way of looking at it when you look into scaling up of reactions. And here they have also given a very nice example of how numbering up of the electrochemical cells can give you a very good scalable version of it. There are only 3 electrochemical cells over here, there are 4, and there are multiple numbers. So based on that, you have a higher amount of scalability that is happening simply by numbering up, which is a very important and a very nice way of looking at how electrochemistry could be helped in scalable flow. Going further, biocatalysts is also a very novel and a very upcoming domain these days in flow. So as we can see over here, you have a reaction that is enzyme catalyzed. So those enzymes could be like placed through a flow reactor and you can have a reaction happening. So over here, it's a green reaction and the reaction time is about 20 minutes. It requires only mild reaction conditions. And most importantly, it's a versatile or a generic procedure. You could apply these kinds of methods similarly to various other biocatalytic reactions as well. So where we'll have a very good extrapolation of one method to other, thus creating robust ways of working with reactions. And these sort of reactions have a very problematic issues when you do typical batch chemistry because enzymes can get deactivated very quickly and they are extremely sensitive. So when we do them through flow, you have a much more accurate control exerted on the process. And the last class of applications that we would be seeing are nutraceuticals. So this is an example of MSM. So basically it is an analgesic nutraceutical. So over here, we can see that this is a typical flow reactor setup that has been reported for this. So we have published this through drills. So going over here, it's very important to see that this particular reaction is a very simple one and a very easily controlled reaction, which doesn't generally happen in typical batch chemistries. This oxidant over here is a very corrosive material. So the handling of this oxidant in a very nice way has been reported. So it's basically a oxidation mediated by metal catalyst free H2O2. So typically these processes involve a lot of catalytic ways of doing it. So that has been avoided over here. And it's a green and a scalable synthetic route with an efficient exotherm management, which comes by means of using H2O2 as the reagent. And the quality of the product developed has a purity of more than 99% with a yield of more than 85% with a throughput of 23.6 grams per hour. So this is a very good example of how flow chemistry has been looking itself and finding out, paving new ways into different modes of science and other domains. So, as a summary of this entire talk, I would like to say that chemistry and chemical engineering have typically been two different fields since a long period of time. So, it's very important that we look into bridging this gap between chemistry and engineering so that one technique can potentiate or facilitate the applicability of the other as well by working together. So, if we can sort of bar this gap, if we can sort of bridge this gap that is happening, we'll be able to get a chemical intensification as well as a process intensification, both of which together can give you a sustainable environment at the last. So this particular thing is extremely important. So I would like to give a few last words on this particular topic. Like, one question is flow chemistry new? So it is definitely not new, though it has been coming into recent picture only now, only recently for the last couple of decades or so. But on the contrary, it's very important to understand that catalytic flow productions of various materials has been in practice since a very long period of time. The production of ammonia through flow happened in as early as 1913. Following that, the petrochemical industry has been doing a lot of flow chemical processes for generating its petroleum based products and the corresponding raw materials. So, flow chemistry is definitely not new. It's just that its applications in chemistry has been very poor, which is currently being taken up very interestedly by various groups, looking at the advantages it has been giving over time. So another important part of the question is how could flow chemistry be made a part of the academic curriculum? Because it is very important that this be brought into the academic curriculum of kids since a very early age in their lives, so that it would be very easy for them to understand and appreciate the value of this particular technology. So, firstly, literature. There are an ample number of literature that is present, which are open access ones. So, you have very good flow chemistry reviews and publications and patents, which work on various parts of the entire flow chemistry. So, it basically gives us a very detailed idea of what people are doing currently in flow. So, reading that is a very important thing. You could also conduct courses, and the courses and classes on the theory and practice of flow chemistry is a very important thing which should be initiated in schools and colleges. Short projects should be initiated, which can give an overview on the practical handling of flow. Workshops should be also conducted, which will help us to independently work on flow. It will teach kids how to construct simple flow setups on their own. And research based topics should be enhanced more in higher levels of research like masters and PhD. So there people would be even more initiated to look into how things work through flow. There are a lot of education packages that come through various licenses. So even those could be studied on understanding how flow processes could be developed. And finally, rather than simply studying and reading all these things, it's very important to actually start with simple tools in hand so that we learn on our own how to optimize, build, and rebuild flow reactions. So these could be a very basic way of how we can start bringing this very vast but important field into the academic curriculum of students. Now, before I conclude, I would like to give a very small introduction about the institute that I am in. So, basically, we are from the Flow Chemistry Technology Hub. So, this is in partnership with the government of Telangana, Dr. Reddy's Laboratories, Laurus Labs, and Dr. Reddy's Institute of Life Sciences. So, just a very brief idea about what BRILS is. It's basically a joint venture or just like a gap which needed to be bridged between the public and the private sector. So between the government of Telangana and the University of Hyderabad in partnership with Dr. Reddy's. So this is basically what BRILS is. And the areas that we focus over here in the flow chemistry technology area is faster, cleaner, and safer reactions, rapid reaction optimizations, easy scale up and smaller footprints of reactions, and integrated synthesis, workup, and analysis. So these are the basic areas of focus that we basically look into over here. Also, the flow chemistry technology hub from which I actually belong. So that is basically a sort of where you look into not just the reaction or the chemical aspect of the reaction, but you also look into the engineering aspect of it, which is the reactor. And finally, you also map both of them together based on the chemistry and the engineering. So that gives you a holistic perspective of how to take a reaction from a typical batch level or a typical ground level to a manufacturing scale. And these are the various reactors that we possess here at the FCT Hub. So this is basically a DART reactor or an AutoChem reactor. This is an ATR or an agitated tube reactor. This is an ACR or an agitated cell reactor and a Laptrix. So, and also Vaportech. So these are basically the various reactors that we have. So the DART and the ATR and the ACR are slurry based reactors. The Vaportech and the Laptrix one are homogeneous phase reactors. And also, we also have different sort of pumps like the syringe pump, the slurry pump, and the SF10 pumps, which are very important for delivering the fluids into the reactors. So these are the various tools that we have here. Uh, basically, the motto of the FCT Hub is to brainstorm, identify, demonstrate, and develop, or the bid strategy. So what we basically do is look into is adapting flow processes for pharmaceutical specific reactions, supporting industry partners to shift strategically into sustainable and reproducible manufacturing. We also encourage multi-industry centric participation and promote seamless scientific interactions between personnel. And most importantly, the focus is on the reaction and not on the product. So that gives us a generic applicability. We look into how we can widen the horizons of various reactions by looking at the generic problems that can arise from process to process, not just based on the reaction. So, uh, hence, this is a very brief idea about the entire parts of flow chemistry and its various ideas. So, the further insights into flow chemistry as a synthetic tool for API or medicinal synthesis and organic molecule synthesis and process intensification or basically scale up of flow and process analytical tools, all of these things would be covered by the very eminent speakers that are further in the line of this webinar. I am extremely fortunate and extremely happy to be introducing them like this. So I really wish that all the students who are visiting this webinar, who are seeing it, will gain a lot of insight into what flow chemistry is, and from all the other eminent speakers that will be addressing you all today. So finally, thank you very much for your attention.
Thank you, Dr. Karuna Veermani, for your very nice keynote address. This is what is actually required for our student community. You have given very right insight into this field. You have
Thank you.
covered both hardware and software aspect of this flow chemistry. The software aspect is the the Clapeyron equation, which is modified, I mean, applied into this flow chemistry in an efficient manner to get the products in an efficient way, pure way, with cost, I mean, less time, within the less time, by equal uniform distribution of temperature, whatever the crux involved in the chemical reactions, they are managed very well through this flow chemistry. And that both the hardware and the software part of this flow chemistry, you have covered very nicely. And if there are any questions, we have some 2 3 minutes. Madam will very happy to take the questions and answer the question.
So, if you guys have any questions, you can put out in the chat box, which will be putting up on the screen. So far, we haven't received any questions. Once it comes, we can directly put it on screen, and then ma'am can take it forward.
Can we get any books regarding flow chemistry? Sir, am I audible?
You are audible, ma'am. So I'll display other questions. You can take the questions. You can start answering them directly.
Yeah, sure. So, hello Nagaraju. It's nice to see your question. So, there are a lot of books regarding flow chemistry. So, basically, there is a professor called Junichi Yoshida. He is a very eminent. I mean, he was a very eminent scientist in the area of flow chemistry. So there are a lot of books that he has written on flash chemistry and flow chemistry and how you can tailor time dependent on flow. So there are a lot of books by Yoshida. So you could like look into the internet for them. And there are a lot of review papers which also speak on the very basics of flow chemistry. There are flow chemical stalwarts like Professor Peter Seeberger and Ian Baxendale and Oliver Capet, etc. So these professors have given a lot of review articles on the field, how they are like combining flow with various other parts of the synthesis. So you could like look into all of them. Like they are very easily available online, and you would be having your own college licensed softwares, right? For your, I mean, for your library. So through that, you can like very easily get those books and papers. So I suppose I have answered your question. If I have not been clear, would you please like write back?
I think no other questions from the student side, ma'am. Let me check.
On author name, okay. Yoshida. Where do I write that? I mean, is there a place where I can write so that he can see the spelling?
So you have a private messaging here section on the right hand side of you where you can chat in, and then it will display it on the screen.
Oh, okay.
So you can send it to me, and I'll directly stream it out.
Yeah, sure. Uh, sir, how do I like write on this? Like, I mean, I'm not getting a place where I can type anything.
Where you can directly write it.
Sorry, sir.
Purpose where you can write in the message, and that will be directly broadcasted to the students.
Um, right. Um, sir,
Or you
actually,
can just tell me the spelling. I'll write it down.
yeah, sure.
Sorry.
Y, Y,
Okay.
O,
Hmm.
S, H, I,
Yes. Hmm.
D, A.
You can see on the screen, ma'am.
Right. Thank you, Nagaraju.
Yes, am I audible? Am I audible?
Yeah,
Okay.
yeah.
Yeah, there was some power issue here. It is now resolved. I am back again. Madam, thank you very much for covering
Yes.
the vast gamut of this flow chemistry in a very short time. And definitely, you have given us an opportunity to explore this further through the collaborations, linkages, and through a continuous association with you. Definitely, we will see that this will be introduced in the as an academic in the colleges and universities in the days to come. Thank you very much for sparing
Thank you.
your valuable time and giving your valuable insight into this very emerging field of flow chemistry. Thanks a lot, ma'am. Okay.
Thank you.
Thank you. Now we will move on to the next speaker, who is Dr. Vidyacharan. I must inform the participants here, Mr. Vidyacharan, he is now giving us, addressing us from US. It is very late midnight there now in US. And even though it is so late midnight, he has agreed to spare the time for the cause of academic and to help the student community in this academic pursuit. So we are really grateful to you, sir, for taking the time. And at this night hour, you have agreed to join, and for that we are really indebted from the all the host institutions and the management. And before we start up the uh, talk from Dr. Vidyacharan, I would like to give a brief introduction about Vidyacharan. Vidyacharan Shinde completed his PhD in the year 2016 under the guidance of Professor D.S. Sharda at Indian Institute of Technology, Hyderabad. During his PhD, he worked on development of sustainable CH activation strategies for the synthesis of novel bioactive heterolytic scaffolds. After his PhD, he worked as a research scientist at Indonesian Research Lab, Hyderabad, India. There, he worked on synthesis of key precursors of drug scaffolds. In 2017, he joined Professor Dong Pyo Kim's research group as a postdoctoral research associate at Pohang University of Science and Technology, South Korea, where he focused on photoredox catalysis, ultra-fast reactions for the synthesis of bioactive scaffolds using continuous flow technology. Presently, he is working as a research scientist at project lead at Medicines for All Institute, Virginia Commonwealth University, Richmond, Virginia, USA. During his stay at M for All, he worked on generic medicines, which is essential medicines for the society. He also successfully tech transfer for the API in continuous flow synthesis by driving down the production cost. With this credit, he published more than 20 publications in high impact journals, and he has had patents also. He is also working as a reviewer for the various ACS, RSC, Science Direct, and Wiley journals. Also working as an editorial board member for the Life Research Journal and Journal of Multidisciplinary. Today, he is going to talk on application of continuous flow in the synthesis of APIs, active pharmaceutical intermediates. With this brief introduction, I present before you Dr. Vidyacharan from US, and over to you, sir, to give your talk.
Yeah, can you hear me?
Yes, sir.
Yeah,
We can.
thank you for kind introduction, Dr. Hiralal. So thanks for giving me opportunity to present like some of the flow chemistry work. And yeah, it's a very late night, so it's already 1 a.m. for me. So this is the title of my today's talk, that is the application of continuous flow chemistry for API synthesis. So these are the few contents of my today's talks. So I will quickly go through the introduction about the flow chemistry, because already Aruna has covered all the introduction part, but I will quickly explain like how this flow chemistry is important compared to the batch process. So then I'm going to talk about the flow photochemistry application for drug scaffold synthesis. And then for like I'm going to talk about the like real chemistry where we have transfer this technology, like this flow chemistry technology for the API synthesis, and which is going to synthesize for the kilo labs and pilot plants. So with this, I will conclude my today's talk. So we can see here that already she has explained about each and everything. So, but even though, so just I will quickly go through this. So the traditional the traditional organic reactions generally will perform in the batch reactors. So where we'll feed the reagents and mix it to well and left it to react over the time. But the product collected after the completion of the reaction. So typically for the batch chemistry, so these are the key factors. So to have the efficient yields, so first one is the concentration and mixture and temperature and reaction time. So when you coming to the flow chemistry, so generally the reagents pumped into the reactor in continuous fashion, and the reaction occurs throughout the throughout the length of the reactor, and the product can be continuously removed. And generally the reaction time in the continuous flow, which is referred as a residence time. So this continuous flow chemistry, so it has several advantages. So like because of the higher surface area to volume ratio. So because of this, so we can see here, I am going to show one of the quick examples. So when you take the batch reactor, so we can consider this is as a flow reactor. So if you have same volume of the batch reactor and flow reactor, so the surface area to volume ratio in the case of flow, it is much more higher than batch. So if you have same volume of the reactor. So due to this flow chemistry having several advantages in performing the reactions, so which is giving the safer reactions and a rapid reaction time, higher safety, and it has the better, because of the better heat and mass transfer, and which is giving the high selectivity of the products. So these are the various advantages of the flow chemistry. So with this, so I will show, like already she has shown the typical example of the flow setup, but I will quickly show like what we are doing in the presently in the lab. So not just whatever the setup is there, so just we are not showing this here. So we work on this. So similarly, we have performed in our development in the synthetic organic lab. So when you see here, so these are the reagents. So we can feed with the pumps. So this is the mixing zone. So this part, it is very, very important to before going into the reactor. because if you have the efficient mixing here, so if you don't have the efficient mixing here, so the reactions are not much efficient. So if you have very good mixing, so the reactions are much more efficient. And this is the reactor. So these reactors we can use as a different reactors. So depending upon the homogeneity of the depending upon the reaction nature. So if you have the homogeneous, we can flow this reaction into the plug flow reactor. So that is a kind of tubing reactors. So if you have like heterogeneous, like if you have the inorganic salts and organic solvents, so such cases we can use the CSTR, that is the continuous stir tank reactors. And if also we can use for the like packed bed reactors for the catalysis. So after the reaction, so we can analyze in line, so the reaction is completed or not. So right now in our lab, so we are using flow IR and inline NMR and inline HPLC. So once we determine the reaction is completed, so we can quench the reaction by quenching reagents. So then we can monitor, like we can monitor the we can monitor the pressure of the reaction by using this back pressure regulator. And we can separate the argon, like when we are using the quenching reagent, suppose if you are using aqueous phase, so we can separate the aqueous and organic phase. So then we can purify and get the product. So this is the typical setup, and based on the reaction conditions, we can interchangeable this part. So generally, like in the flow system, so these are the typical systems which already she has shown these kind of things. So these are the pumps, so which can useful for the feeding the reagents, and these are the mixers, and these are the reactors. You can see here these are the PFR reactors called as a plug flow reactors, and these are the packed bed reactors. So which is useful for the like suppose if you have the like inorganic base, suppose K2CO3. So if you want to use K2CO3 in organic solvent, it is difficult to flow into the PFR reactor. So such cases, we can fill this K2CO3 into this kind of packed bed reactors, and we can run the reactions. And these are the back pressure regulators. It is much more helpful for going the higher, like less boiling solvents, going for the higher temperature. And these are the few commercial available equipments. So we can see here, these are the VaporTech and Series Asia. So right now, like we have this kind of instrument in our lab, and we have also recent advanced reactor, that is the Carling reactor. Also, it's present in our lab. And with this, I'm going to show real application of this flow chemistry in one of my project, where I use like in the photochemistry. So in this project, so we have developed the continuous flow organophotoCatalysis for direct arylation on 2H indole system. And based on this chemistry, we have scaled up this reaction by designing the new reactor for the synthesis of one of the drug scaffold, that is the liver X receptor agonist for the cardiovascular diseases. And by developing this photochemical reactor, and we have run this reaction for the 1 hour reaction time. And in this case, so we have the productivity 3.75 grams in 1 hour of reaction time. So recent days, this photochemistry has played a pivotal role in the organic synthesis, because so when we run this photochemical reaction in the batch, so the penetration of the photolight is not efficient because of the less surface area. So when you see this Arrhenius equation, so like based on this, so if you run this reaction in the capillary, you can see the light intensity, the penetration of the intensity is much more higher than the batch. So because of this, so like as I earlier mentioned in the introductory slides, it is having the higher surface area in the continuous flow system. So because of having higher surface area, so the penetration of the photolight is much more efficient in continuous flow system. So and having the equilibrium control exposure time. And in the flow, so if you run this reaction in the batch, so the flammable solvent, like high amount of flammable solvent, it is near to the lamp. But in the case of continuous flow, the small amount of flammable solvent near to UV lamp, LED lamps. So and it is easy to scale up. So with this, so like when you're coming to the novelty of this reaction, what is the novelty? Like why we have picked this reaction? So when you see the literature background on this 2H indole system, there are reports. So they have developed with the like metal catalyst and external ligands, and they have used the harsh reaction conditions and longer reaction time. So by taking this challenge, so we wanted to avoid this metal catalyst. So we wanted to use the organic dye, which is the like environmentally friendly catalyst, and we wanted to run this reaction at milder conditions. So that's what we have expected, and we have performed. So successfully, we have achieved this reaction. We also involves a photocatalyst for the direct arylation at room temperature. So all these approaches so proceeds through the ionic mechanism, but our approach so proceeds through the radical mechanism. To get expected this arylated products, so we have screened the different photocatalysts and different solvents, and unfortunately we could not able to improve the yield more than 50% in the evosin-Isaac photocatalyst. So then we have tried with the different bases. So among the bases, we have observed the DIPA. That DIPA is a more suitable base for this reaction. So, and for the reaction time is 18 hours. So if you are, then we have screened like different equivalent of base to increase the yield of the product. Unfortunately, we could not able to increase more than 65% of the yield. So as I explained, to take the flow photochemistry advantages, so then we thought we can run this reaction into continuous flow. Then we decided, so we have taken like 2-meter length of the capillary tubing, which is having the like 0.25 mm dia, inner dia. So then we have run this reaction at different flow rates. So at 100 microliter per minute, so we have only 1 minute of residence time, and the yield of the product is 74%. And if you decrease the flow rate, so up to 25 microliter per minute, so the reaction yield increases 76%. If you increase, if you decrease, still decrease the flow rate, but we could not able to see drastic increasing in the yield. So based on the time concern and yield, so we have picked 100 microliter per minute as the optimum condition for the check for the scope of the reaction. So when you see the same reaction in the batch, so it takes 18 hours of reaction time. But when we perform similar reaction in the flow, so the reaction time is only 1 minute. So the reaction time is drastically decreased from the hours to minutes. So after having this optimized condition, so then we have screened the different scope on indole system and diazonium salts. So in all, like we have checked the electronic effect and almost all the cases. So we have very good yields in the case of flow rather than the batch. And similarly, we check the scope with respect to the diazonium salt. So here also we have the very good yields in the case of flow than the batch. So to further check the scope of like to applicability of our protocol for the different heterocyclic system, so we have screened the different heterocyclic systems, but unfortunately, this kind of heterocyclic system did not work our optimum condition. So as this methodology we can apply for the drug scaffold synthesis. So we have synthesized 2 different drug scaffolds, that is the liver X receptor agonist for the cardiovascular diseases. So we have taken the suitable substrate on the indole system and aryl diazonium salt, and we perform this reaction in the batch as well as in flow. So we have very decent yields in the flow. So with this, so like after successfully checking the scope and for the drug application, so then we thought, so what is the mechanism? So because like many students don't know about like photochemistry. So but I'm not going briefly about, because it is a like very lengthy process about the explaining, but just I'm going quickly. So how the mechanism it happens. So we have did some of the control experiments to prove this mechanism. So when we perform this, so this is the optimum condition. So when we perform this reaction without photolite and base and photocatalyst, so there is no reaction. So if you perform only in presence of photocatalyst, so we have only 3% of the yield, and in absence of photolite, photocatalyst and presence of photolite and base, we have 7% of the yield, and in absence of photolite, so we have only 10% of the yield. So based on these results, we can conclude that for the reaction, so photocatalyst and photolight and base is necessary for to getting the expected product. So as we are, as I have shown, so our reaction it is proceeding to the radical mechanism. So to prove that, so we have tried this reaction with the radical scavengers. So and when we perform this reaction with the radical scavenger, we did not see the expected product, but we have seen the tempo trapped radical formation, radical product. And we can see here, this is the reduction potential value of the eosin-Y, and this is the oxidation potential value of the DAPM. So when we see, so in photochemistry, so the quencher is picking the quencher is very important to have the very good yields. So as for our reaction, so DIPA is the quencher. So we have proved that one by fluorescence emission spectroscopy. So when we try the fluorescence emission spectroscopy, so with a different concentration of the diazoxide salt with the eosin-Y, so there is no change in the fluorescence intensity. Whereas when you screen with the different concentration of the base, so there is a drastic decreasing in the fluorescence intensity. That means the DIPA is the quencher of this reaction, and which is participating into the single electron transfer event, electron transfer event. So based on this all results, so we have proposed the mechanism. We can see here. So initially, the eosin-Y in presence of photolight, it get excited state. So then takes the electron from the base to form radical anion. So this radical anion takes the electron, gives the electron from the diazoxide salt to form this phenyl radical, and from the form a regeneration of the photocatalyst. So then this phenyl radical attack on the C3 position of the 2H indazole system to form this radical, and which is giving the electron to the base to form this carbocation. So this carbocation undergo into the rearomatization to get the final product. So here we can, there is a possibility of getting the biphenyl product formation. So we have observed that biphenyl product formation, but this reaction is more competitive than the biphenyl product formation. So that's what this reaction is more straightforward than the biphenyl formation. So as this catalyst, that is the eosin-Y, so that is the organic dye. So after the reaction, we cannot recycle this photocatalyst. To recycle of this photocatalyst, so we wanted to immobilize this photocatalyst inside the capillary tubing. So I am not going to talk about all this. So this is like some depth concept. So, but I will give quickly information about this. So this eosin-Y, we have immobilized inside the capillary tubing. So by developing the pre-ceramic layer on the capillary surface. So we can see here, this is the eosin-Y structure, and we have developed the amine functionalization on the inside the capillary tubing. So this amine and acid get coupled to form this amide bond. So then we have confirmed, like the immobilization we have confirmed by IR spectroscopy. So we can see here the clear amide bond formation. So with this capillary tubing, so we can see here, so this is the 1 meter length of the capillary tube, so having the eosin-Y immobilization. So with this capillary tubing, so we have run the reaction, so optimum condition, which we have got in the previous case. So we have screened with the different flow rates, and we have picked like 200 microliter per minute as the optimum condition, and we got like 62% of the yield, and the residence time is 0.63 minutes. And to know this reaction, to know the recyclability of this tubing, so after the reaction, so we washed with the ethanol, and then washed with the water. So then same tubing we have used for the like 5 to 6 cycle, and we can see the yield of the product from entry 4 to 9. So almost all the cases we have similar yields. So based on these results, we have concluded that so there is a no leaching of the photocatalyst from the capillary tubing. So as there is no leaching of the photocatalyst, so then why can't we can build up the photochemical reactor? So based on this concept, so then we have collaborated with the chemical engineering people. So we have fabricated the photochemical reactor. So we can see here, these are the 10 different capillaries, so aligned with vertically in the quartz tube. So this is the flow distributor and collector, and we have did the like CFD analysis for the flow distribution. It should have the uniform distribution of the solution from the inlet to outlet. So we can see this graph. So almost all the 10 outlets, we have the uniform distribution. So with this fabrication stuff, so then we have integrated the system. So this is the quartz tube, aligned the all the capillary tubings vertically inside the quartz tube and stepped with the visible light. And we wrapped with the aluminum foil, having the efficient irradiation to the reaction. And we have the fan inside to, like, when we have the longer reaction time, there is a lot of heat generation. So to cool the reaction, so we have fan inside the reactor. So then we can start pumping the reagents from the down, and we can get the up reaction mixture. So then we have the integrated system, like a workup process. So it is like 2.2 minutes it takes for the workup, and the reaction time is like 1 minute. So total like 3.2 minutes. So we can get the like separation of the organic and aqueous phase. So we can see here. So this is the inlet going through the quartz tube, having capillary tubings. So this is the outlet. It will go through the workup system. So we have the like ether and aqueous phase. So here we can see here in this tubing. So the organic and aqueous phase, like it is showing like bubbler kind of thing. So then finally we can collect the organic and aqueous phase and separate by separating funnel organic and aqueous phase. So evaporate the organic phase and get column chromatography. So in this case, we have the productivity like 3.75 grams in 1 hour of reaction time. So next, I'm going to talk about like real application of this flow chemistry in industrial applications. So actually, what is our main ambition, like using this continuous flow chemistry? So as you know that recent COVID times, so how we have faced about the drug shortage in the market. So during that time, so the US government, so that is the federal government, came up with the new funding source for the generating the generic medicines with lower cost and easily accessible to the society. So based on this concept, so we started our work in continuous flow chemistry and developing the small scale to larger scale and further process development. And we are going for the kilo labs and pilot plants with our industrial partners. So what we are doing basically in the lab is, so we'll develop the reactions in batch as well as in flow, and we'll find out the like exact conditions like a stoichiometric material balance and everything. So which reaction is more, which step is more suitable for the flow, and which step is more suitable for the batch. So we'll run this reaction, and we have work with the design experiments. And with this design experiment, we have perform like we will perform like several reactions. And with this, so because of the confidentiality issues, so I am not going to I am not showing the exact structure of the molecules. So this is the one of the drug, so which is which we have like 5 steps. And our previous M4All process has the like $200 per kg, but so we wanted to reduce this cost of the API. So but we have used this similar process to transfer into the flow. So unfortunately, this process did not work in a continuous flow system because we have the lower productivity, even though it works, and the results are not consistent. So we have the reproducibility issue. So then we have reinvestigated the route. So by reinvestigating the route, like we have changed the starting material to get the expected product, and we wanted to avoid the clogging issue during the different steps. So then we have like to quickly go forward. So we have the design experiments, and we perform accordingly the several experiments. And with this, so we have like out of 5 steps. So because when we are performing this reaction, so it is not easy to perform each reaction into the continuous flow system. So there are several challenges to perform this reaction into continuous flow. So if you take the batch chemistry, we can do simply any kind of reactions we can do in the batch, but it is not possible in the flow. So that's what, like, we started the 5 steps. So some of the cases we have like very clogging issues. So those steps we are running in the continuous stir tank reactors. So among the 5 steps, so we run the 4 steps in the continuous flow, and the first 2 steps in the plug flow reactors, and third and fourth steps in the CSTR in continuous fashion. And last steps, after 4th step, so we have isolated the product and we run the last step. Because so in the when we are going for the API synthesis, the impurity formation is very, very important, because if you have the impurity, so your process cannot sell into the market. So, and this is the USP specification. So we should meet the specification of the USP if you prepare any drug in drug in the batch or flow process. So because of this impurity profile, so first 4 steps we have run in the flow, and last step we run in the batch. So first 2 steps we have optimized in the flow. So then we run this reaction for 1 hour of reaction time. We have the productivity 50 grams per hour. And so whatever we are doing this reaction, so we have to be prepare the batch sheet. Like batch sheet means like we have to give the commandings, like we have to make the commandings. So it should be work for anybody. So they should have the similar results. So that's what we have worked. Like we have performed the similar reactions like 4 to 5 times repeated. We have consistent result. And with this process, we can able to take the cost of the API from $200 to less than $100 per kg. And we met the USP specification. And with this, so I am going to show one of the video of the like how we can go for the larger scale this flow chemistry. So we can see here. So we have the first 2 steps. We have the 3 reagents. So we can see here reagent 1 and reagent 2. So we can get intermediate, and this intermediate will react with the reagent 3 to get the drug intermediate. And from this, so we are going for the 3rd and 4th step. So I'm not going to talk about the CSTR system because some of the confidential things are there. But just for the quick information, so you can see here. So these are the different pumps. So 1, 2, and 3 pumps. So we have the inlets here. So reagent 1 and reagent 2. So this is the T junction, like this is the mixer. So we can see here, first one is the PFR reactor, which is having 20 ml of the volume, and the reaction temperature is 130. So and after this reaction, so intermediate, so we have the another inlet, so 3rd reagent, so which is coming from this 3rd pump, and it will mix in this T junction. So after this, it will go to the another 10 volume of PFR reactor. So this is at room temperature. So then it is going with the BPR. So because so here we are running this reaction at 130 degrees temperature. The reaction solvent is acetonitrile. So generally the acetonitrile boiling point is like near about 83. So if you run this reaction at 130, so just it will be boil up. So to make the acetonitrile into the solution form, so the back pressure it is helping. Back pressure is very important. So this is the setup. So we have like you can call as a like lab made reactor. So then, so you can see this video. So these 2 reagents going to the reactor, and first reactor, that is the PFR reactor, and after the intermediate, so then it is going. So another reagent is coming here. So it is going for the 10 ml coil reactor, and we have the product here. So then we have separated this. So to have this consistent result, so as we have made this reactor in the lab, so how this reaction it is suitable for the commercially available equipment. So that application also we have shown here. So this is the VaporTech instrument. So here we have the 2 pumps on the VaporTech. and this is another pump. So we'll feed the two reagents from these two pumps, and which is going for the first reactor, which is having 20 ml volume. So then after this, coming from the outlet, so then another reagent is mixing with the outlet, and it is going for the another reactor. It is at room temperature. So here we know inbuilt system. So if you just maintain the temperature, like fix the data on the system, so automatically it will take the temperature and flow rates. And you can see here the picture of like video of this setup. So these are the two reagents. It is coming through these two pumps and going through the reactor, and coming from another reagent from this pump. You can see here, this is the third reagent. So going to the another reactor, 10 volume of the reactor. So we can get final product here. So this is what we have tried, and successfully we have tech transfer this, and now so this process we can run several hours, so there is no issue in the reaction setup. So that's what we have run. So now we are in the process of going for the pilot plant. So with this, I will conclude my today's talk. So as Dr. Karuna mentioned about the flow chemistry, so this is a like enabling technology. So it has big potential for the API synthesis and drug discovery program, but this flow chemistry is an alternative technology for the batch process, but it has its own limitation. But we can overcome these limitations by integrated batch flow system. That means like we can perform some of the reaction in the batch and flow for the particular drug synthesis. So it's generally called as an integrated batch flow system. So it is a very good choice. And these are the funding sources which I got for my research career. And presently, this Medicines for All is giving me a very good opportunity to explore this flow chemistry stuff for the industrial application. And we are very proud to tell that, like, as so when we are working for the one of the drug, so it is a very, very important drug for the, especially for the Indian people. So if you see like every home, each person has, if you take each home, so we'll have one person that kind of disease. So I'm not going to disclose all the details. So each person has the disease. So US government don't have such kind of diseases, but even though we are take that challenge and we are working on that medicine, and which is very, very, very important drug scaffold. So soon we are going to make that success, because in the world only one company is synthesizing the drug, and it is a very, very shortage in the market. So thanks for giving me opportunity to present my work, and thank you. If you have any questions, I am happy to answer.
Thank you, Dr. Vidyacharan. Even though it's a late night, you have taken all pains to explain in detail about the applicability of flow chemistry in the API synthesis, and that speaks of your concern towards the academic needs of the student community, and that you have addressed very aptly. And for that, from on behalf of the organizers, we are really, really indebted to you, sir, for sparing your time and sharing your valuable knowledge in this field, which is going to help our student community in future to shape their careers. Any questions are there? If any questions are there, Abhishek, any
No,
questions?
sir. No, sir. No questions. I request Vidyacharan sir to please stop sharing the screen.
Yeah, sure.
So no questions, sir. No
Yeah.
questions.
So, with this, we have concluded this session, and thank Dr. Vidyacharan again on behalf of all the organizers. Thank you very much. And now we invite Dr. Nagaraj Nayak for the next session, who is going to speak on uh, process intensification in the synthesis of small molecule via continuous flow process. Before Dr. Nagaraj Nayak begin his talk, let me introduce Dr. Nagaraj Nayak. He hails from Karnataka. He is our own man. He is from Mangalore. He has completed his post graduation from Mangalore University with very highest credentials. He is awarded the gold medal for having stood first rank in PZ. Then he did his PhD uh, with CSIR laboratory in on organic chemistry with CSIR NIST scholarship. In the year 2017, he has completed his PhD, and presently he is working as postdoctoral fellow at Indian Institute of Science, Mumbai, and he is working on flow process, continuous process. He has expertise in various aspects of the synthesis of organic molecules, of having a lot of applications in drug as well as sensors, solar cells, and he has published many papers in the international and national journals of very high impact factor, and he has all very nice technical skills in various aspects in more required for the research. Present today he is going to talk on process intensification in the synthesis of small molecules via continuous flow process, and I request Dr. Nagaraj Nayak to give his talk and address the
Yes.
participants. Thank you, doctor, and it's over to
Thank
you,
you, sir.
doctor.
Thank you. Yes. Thank you. Let me check. Am I audible?
Yes, you are audible, doctor.
Yes. Yeah. I'll try to share my screen. Can you screen my see my screen?
Yeah,
It's coming. Okay.
yeah.
Okay. At the outset, let me thank all the organizers for allowing me to speak today. I'm very grateful to you all for giving me this opportunity. So today I'll speak briefly about process intensification for the synthesis of organic molecules via continuous flow. I realized that most of the audience are here are BSc and MSc students, including few research students. I decided,
Sir, just a moment.
huh?
Sorry to
Yes,
interrupt. But you
yes,
have started sharing your web page, right? And if you just share your PPT, that would be fine.
okay, okay,
Also, keep on share your entire screen, and then go to your
okay,
PPT.
okay. Is it better now?
Yeah, sir. Fine.
Fine. Okay.
Yes.
Thank you. So today I'll speak about process intensification for synthesis of organic molecules via continuous flow. I realized that most of the students or the audience are BSc, MSc students and few PhD students. So I decided to keep this presentation as simple as possible. And I took some time to select reactions out, so that the students will not run away from flow chemistry to begin with. Out of 150 reactions that we have optimized, 150 plus reactions that we have optimized for last 3 to 4 years at IIT Bombay, I have selected the simplest possible reaction so that it can reach even a BSc student. Okay, so I'll begin with what all the facilities that we have in our lab. I'll give few examples for homogeneous reactions. Then I'll give you example for heterogeneous reactions. Even I have shown the actual picture so that students will realize what it is than showing the scheme. Then interesting problem. So how to effectively utilize aqueous HCl. Then a little advanced thing I'll introduce, that is something called telescoping. Okay. So these are the state of the art flow facilities that we have in our laboratory at IIT Bombay. If you look at this reactor, this is called Laptrix reactor. The volume of this reactor, the chip reactor, is 1 microliter. Okay, generally in our lab we keep reactions in a RB of 250 ml. Now, you should be able to imagine we reduce the volume of the reactor is 1 microliter. It's easy. You can put this reactor in your bag with these two pumps and go to client site, do flow reactions, optimize, give the data, and come back. Once the reactions are optimized in this reaction, these are float reactors used for the productions. This is called MR260. The condition that you optimized in this smaller chip reactor can be exactly copied into this bigger reactor so that production is possible. This is called H cube, used for hydrogenation of the reactions. This is Phoenix reactor, used for high temperature reactions. It can go up to 450 degree. These reactors already introduced by our previous two speakers. In fact, our previous two speakers made my job very easy. They gave basic explanation of all flow reactors or principles, everything. So I don't spend much time on these two reactors. These are vapor tech reactors and series reactors. So I'll spend time on these two reactors, very important reactors from UK, called agitated cell reactor, and this is called agitated tube reactor. Okay, this is a 100 ml reactor. Here the reactor is here where I have marked it. This is a 10 liter reactor. This is a lab scale version. This is a pilot scale version. So in our lab we have both. In the future I'll show we have optimized the reaction in these two. This is a spinning disk reactor which we generally use for making emulsions. Okay, this emulsion will later polymerize to give to produce high quality polymers. This is called synthetron reactor. Fumi reactor also is called Fumi reactor, used to do butyllithium reactions at room temperature. It's because of again very high surface area to volume ratio, as discussed in the first talk. We do in plant the butyllithium reactions at minus 78 degree because it's highly exothermic reaction. As the temperature increases, you will land up in a lot of side products. However, because of this very high surface area to volume ratio of this reactor, we can simply do reaction at room temperature. Okay. To begin with, I'll start with two homogeneous reactions, which are very common to our BSc student. They are nitration reactions. So I have taken two examples here. So we are using nitric acid and sulfuric acid for generation of nitronium ion, and we are nitrating this position. The only problem is once the reaction temperature reaches 100 degree, this COOH group leaves. Okay, because COH is a gas, the pressure in the reactor builds up, and it's kind of a runaway reaction. Because we all know that nitration reactions are highly exothermic reactions. Because of this, in batch, in the plant, they carry out reaction at 50 degree for 24 hours with a very slow addition of nitrating mixture. And we're not saying that we'll solve everything, all of their problems in a minute, because they're running this industry for last first 40 years and they're very happy about it. However, when they came to us, then we at the end we optimized the process. We could do the reaction at 90 degree within 30 minutes. I don't show the data here because of the confidentiality. But see, from 50 degree to 90 degree, from 24 hours to just 30 minutes. It's nothing magic here. Again, based on the principle that Dr. Karuna explained, nitration reactions are highly exothermic. Batch reactions have very poor heat transfer. In our flow reactors, the generated heat can be easily taken out. So the temperature will be, during the process, it will be 90 to 93 and it will never reach 100 degree. That's the advantage. And second nitration we tried is nitration of benzo trifluoride. So see this, we all know this is a meta directing group. So we will have nitration at this position. But still we will have ortho and para because this again based on our activation energy. Although meta nitro is favored, it's not that ortho and para will never form. Second point here is this is again a very high exothermic reaction. In the batch they carry out at 0 degree, but still they will get 70% meta product. with the meta to ortho para ratios of 4.1. Why do we get 30% side products? It's because as the reaction proceeds, you will have a lot of heat generated, and you can imagine a 10,000 liter tank. There are hot spots inside the tank. That reactor cannot take out the heat easily. So in those zones, temperature will not be zero. It will be, say, 50 degree or 70 degree. At that temperature, these two products are favored along with this one. So that's the reason they absorb a very large amount of ortho and para product in their process, which actually has no commercial value. It's only this product has very huge commercial value. So we actually tried this reaction, and this is actually set up. We have tried this reaction in called reactor called agitated cell reactor. We have pumped this BTF using one of the vapor tech pump, nitric acid using another vapor tech pump, and sulfuric acid using third vapor tech pump. You can see these are the feeds here: feed 1, feed 2, feed 3. Using a chiller, we have maintained the temperature of 30 degree, and we show some representative data. You can see, because in the batch they do it in 6 to 7 hours, we could finish almost the reaction in 1.5 hours. You can see metanitro is around 80%. The point that has to be stressed here is, although yes, the point that has to be stressed here is we are just getting 30%. That means in your 10,000 liter reactor, this 30% turns to be huge, and it's a big waste for the industries, and they're spending money to dispose this waste. So if you increase this from 70% to 80% also, that's a big saving for them. And these are not 100% optimizer results, which I have not shown. As I said, this will be confidential. Also, you can see the ratio meta to ortho plus para is much better than that we get in continuous flow than whatever they get in their plant. So once we transfer these results to them, immediately they will change the setup slowly. If not immediately, they'll slowly change the setup based on their cost calculation to the continuous flow. So after these two homogeneous reaction, I'll come back to heterogeneous reaction. So this is called camphene. This is called isobornyl acetate. This is isobornyl acetate is an important intermediate for the synthesis of camphor, and there are only four industries in the country to which they produce camphor, and their batch are in 10 tons per day. So this isobornyl acetate also finds applications in this kind of commercial products. You can see. So if you come back to chemistry, there is a exocyclic double bond here. This T66 is acid base catalyst. This catalyst will protonate this double bond, and acetic acid will be added to here with small rearrangement. Reaction is very simple. But the problem here is, again, this is an exothermic reaction. The moment the reactor temperature increases above 40 degree, you will start forming so many impurities which are practically not possible to separate. This is the issue. When they approached us, this was the standard. The reaction where they were doing with 1 volume ratio of acetic acid. Here that turns out to be around 5.8 equivalent stoichiometrically speaking. Reaction time was 24 hours with 20% starting material left. Over last 1 year, although I have summarized it in a very small table, this took us for nearly 1 year to optimize the reaction. At the end, we could finish this reaction in 20 minutes. The 24 hours could be reduced to 20 minutes, and the volume of acetic acid also could be drastically reduced. Now, if you can quickly calculate the cost, there's a huge saving the moment we transfer from batch to flow. This is where the students has to get attracted and think that flow is the future. This is the actual reaction setup. You can see this is the reaction mixture, heterogeneous reaction mixture containing acid catalyst, acetic acid, and this compound. Pump using this peristaltic pump reaches the reactor, top of the reactor, and will collect from the bottom. And this shakes this way horizontally, which enhances the mixing. And there is a if you can see the black tube here through which our Julabo chillers, thermal fluid flows, because of which we maintain the reaction temperature 30 degree and it will never go above 40 degree. So again, another simple reaction I've selected here, which is again easy to understand. Benzaldehyde reacting with acetone at room temperature 6 hours is something called Claisen condensation. So this is 90% product and they will get 10% timer. Again, this is a different industry. I have not named them here because of confidentiality. Also, they are in market for last 30 years. They are happy with whatever they get. However, can we still reduce this 10%? That's the question. Because this 90% whatever we are getting has a huge market in flavoring ingredient in food and perfumes. This 10% is practically of no use because they have to burn it, which costs money for the industries. Here, can flow be the solution? The answer is yes. If you understood the initial talk, in the continuous flow reactor, the product moves forward and it does not see the reactant. If you see this, this is the reactant and this our product. And this product continuously moves forward and hence this cannot see fresh benzaldehyde. So the chances of this forming is very less. Small representative result if I want to show here. So we could finish reaction in 180 minutes, which is 3 hours, with only 3% dimer form. Industrially, they are having 10% dimer. In our flow setup, we are getting only 3% dimer form. So there is a 7% saving. Again, it is not a 100% optimized data I am showing because there is still 7% benzaldehyde left. And you can see we have reached benzaldehyde and acetone already 90%, which they were anyway getting in their batch. This is again actual flow setup. This is the slurry of barium hydroxide which used as a base here. This benzaldehyde and acetone were pumped using Vaportec pump and they reach this tube reactor which is called ATR, which is a 350 ml reactor. The results are shown here. So this can be directly scaled up. We can have a pile of 4 tubes on this. So this 350 into 4. So the next version is available is 1.25 liter. So we can have 8 of them. That is 1.25 into 8, which is 10 liter. So that this data whatever we are getting can be exactly reproduced in that 10 liter reactor, and that data can be again reproduced in the next version of the reactor, which is again commercially available, called rotating tube reactor, which is a 100 liter reactor. If you have multiple of 5 to 600-liter reactors, whatever the problem the industries were facing for say last 10-20 years could be solved. Then again I could pick up another interesting thing which is simple here. What to do with aqueous HCl? Because this industry which generates 80 tons of aqueous HCl per day. The question is what to do with this, because right now they are selling this at minus 4 rupees per liter. What I mean is someone is taking HCl from their factory and factory is paying them. That is, for disposal is very expensive. So open market is very less. We may think that HCl we will use in our lab, but in lab we use 100 ml to 1 liter per day, but here 80 tons per day is the production. What to do with this? There are solution possible. So HCl in aqueous medium can react with glycerol to give this 1,3-dichloropropane-to-ol. Okay, this 1,3-dichloropropane-to-ol in the presence of base, this can generate, we can just recall our chemistry, you will get this kind of epoxide ring here, and this has huge market. These epoxides has huge market for making epoxy resin. So the only target is, can we consume HCl? Okay, if you look at literature, glycerol can be completely converted to dichloro using 8 equivalent HCl at 140 degree under continuous flow. But remember, this is not our objective. Our objective is we want to completely consume HCl. Here, stoichiometric requirement is 2 equivalent of HCl, but they are using 8 equivalent of HCl to push the reaction and they are getting it. Fine, it's well and good. However, our requirement is not that. We want to, again I am repeating, we want to completely consume HCl. What we did, we took glycerol, HCl and catalyst, and standard PFA reactor in vapor tech reactor, whatever we have shown earlier. Then there is a back pressure regulator to keep the reagents intact, and we collect. This is the schematic flow setup. There is large excess of glycerol here, so 4 equivalent of glycerol and 1 equivalent of HCl. At 140 degree, we found that only 1.6% of HCl is remaining. We started with around 23 to 24% of HCl, which is the waste from the industry. We made it to react with glycerol with very large excess of glycerol. I mean 4 equivalent of glycerol. At the end, whatever is coming out is 1.6 equivalent to 1.6% HCl. That can be easily treated in the plant because it has only a small amount of HCl. But chemistry wise speaking, because you are having large excess of glycerol and less acetic acid, HCl, you will not be able to have complete conversion to dichloro. We will be selectively getting only monochloro, but that is fine. This monochloro can be later converted to dichloro, but our objective to consume completely consume the HCl is salt. So this we tried in 3 months, and this whole project and the technology was transferred to the industry. Finally speaking, so I'll speak something little advanced also, which we do here, something called telescoping the organic reaction, which again Karuna introduced in her introductory talk. In telescopic reactions, we do not isolate the intermediate. So whatever the product formed in the first reactor will be directly pumped into the second reactor, and so on. Here, see, this is the monomer, and the polymerization is happening in the first reactor. So this reactor will give you polymer at this junction, which will mix with second monomer, and this second polymerization happens in this reactor. Whatever the outlet comes out from the outlet is a diblock copolymer, and this continues. And at the end, we get from this fourth reactor outlet is a tetra block polymer. The beauty here is you're not isolating the intermediate at any stage. You're just pumping 4 reagents and collecting the product at the end. It's not so simple as I said, because I'll come to my own reaction and I'll tell you the difficulty there. And this is the reaction that we have optimized. This is the polymer which has very huge market again, because these are called class of polymers called conducting polymers. Conducting polymers find diverse applications in thin films and displays because of their electrochromic properties. Commercially, this is made by this this polymer is made, which is shown in this scheme. Okay, first step is alkylation here, or so you have CH2Br, sodium hydride, and a alcohol. Okay, so the anion will be generated in the alcohol. That anion will come and attack here. So you have basically put alkyl group here. Okay, something called Williamson etherification. Then sulfuric acid or any acid basic catalyst, you are basically deprotecting this group. We'll take out this group and make this dihydro OH group free. Okay, once that is done, then you under this you do is transesterification in the presence of acid catalyst. It's called silica sulfuric acid. What happens is that methoxy group will be replaced by this OH to give this product, and the side product here is methanol. Okay, then once that is done, you just polymerize this at these positions by oxidative polymerization. Okay, which is shown here. So this is the standard reaction. First we optimize this under batch, then we optimize each step under flow. Each step in the sense, yeah, I can show here. This first step will be optimized under the only this condition. Okay, once the product comes out from this, after optimizing in terms of pressure, temperature, concentration, and time, then only we will connect the outlet to the second reactor. Okay, needless to say, this reaction was also optimized separately. Okay, this goes in these sequences. Okay, so again, if you remember the section as I explained, first reaction is alkylation. You pump these 2 reagents using one pump, and sodium hydride another using another pump. And the first reaction we could achieve in 20 minutes at 120 degree. Okay, the outlet was connected to the another reactor where it meets with sulfuric acid, and the deproduction takes place in this reactor in 30 minutes. Okay, then we want the next reaction to be done in toluene, right? So we introduce toluene in between, so the product dissolves in toluene here in this reactor. Okay, so now we have aqueous phase as well as toluene phase. How do we separate it? Commercial liquid separators are available, something called Zyputh reactors, which they will separate on aqueous and organic in line. Okay, this is represented by Z. So this will split into two. The aqueous waste will be collected here, which will be discarded. The organic waste no, is not waste. The organic layer which contains the product will be collected here. Okay, that will be pumped into this next column, which is filled with water absorbing zeolites. Okay, because a moisture of what a small amount of moisture present also will not drive this reaction, if you understand chemistry here. So we have to take out all the water present here, so water will be absorbed in line. Your DMT, or this one methoxythiophene, will come from this pump, and the reaction will take place here at 120 degree within 15 minutes. Okay, so now at this outlet what you have is this product you pump into this reactor. From here the oxidizing agents, and the oxidizing agent that we use is FeCl3 methyl acetate. Okay, this monomer is coming from here, the oxidizing agent is coming from here. Both of them will react at 70 degree. Reaction can be completed within 15 minutes. What you get out is the polymer. So this is something called telescoping of the reaction. In between we can monitor whether the reaction is going to complete or not, which we do by Mettler Toledo inline IR as well as inline NMR, which I have not shown here, which makes the understanding little trickier. So at the end, I will acknowledge Professor Anil Kumar for introducing me to this fascinating area of research, because I came from a background where we were doing batch reactions, and when I entered here, I was like, everything is new, but it was kind of drastic transformation for last 3 to 4 years here. So I wholeheartedly thank Professor Anil Kumar for allowing me to work in this area, and IIT Bombay for providing the fellowship, and all my teammates for their constant support. Thank you. Hello, am I audible?
Yes, sir, you're audible.
Yeah. Okay. During my presentation, was there any breakup? I did not check in between. I'm sorry.
No, sir,
Or
it's
it was
fine.
it was
It's good.
continuous. Yeah. Okay.
It's
Okay.
continuous.
Thank you. Yeah. If there are questions, I am okay to quickly answer.
Okay. Madam, you get me for us then, right? Yeah, sir, don't just let me check out the questions.
Yeah.
No questions, sir. No questions from
Right. Right.
users.
Yes. If there's something, students can contact me anytime later. I will be available. So no issues.
So, on behalf of the organizers, we thank Dr. Nagaraj for giving insight into the flow chemistry, taking very few simple examples, and how it can impact the industry when it is applied, and it can reduce the cost, it can reduce the time. That is the impact of this flow chemistry that needs to be understood by our students, so that they can be well versed to join the industry and take up the challenges of cost reduction and efficient production of the required products. So, thank you, Dr. Nagraj. We will be in touch with you for our
Thank you.
future programs
Definitely.
to
Definitely,
help
sir.
the student community and to improve the academic curriculum of the UG, PG, and research level. Thank you very
Anytime.
much.
And thank
Thank
you,
you.
sir.
Thank you
Thank you.
very much. Now, with this, we go move on to the next session that will be addressed by Dr. Arun Nikam. He will be going to speak on Arun Nikam, flow chemistry
I
for the
cannot.
synthesis of organic molecules.
Yeah.
Hello,
Yeah. Yeah.
Arun.
I cannot access the video like camera. I don't know.
Oh, that will be, you are using laptop now, sir.
Yeah. Yeah. Laptop. Initially, I was able to access, but now it's. I don't know.
That will be, yeah.
So I
Uh,
can share the slide also. No
slides.
problem.
Okay, okay. Uh, Before we take up the next session by Dr. Arun Nikam, actually he is on traveling, he is on industrial visits, but because of our request and the commitment he has given to us organizers to address this webinar, he has taken time out during his industrial visit schedule and addressing us from wherever he is, in whatever industry he is. And Dr. Arun Nikam is a has completed his PhD from CSIR NCL Pune. During PhD, he has studied flow chemistry for nanoparticles. Then he pursued his postdoctoral studies at Postech, South Korea, where he worked in focused on translation batch chemistry into continuous flow for organic molecules. He has established his own consultancy firm, Navi Archem Technologies, and working with various industrial partners for developing scalable process for organic molecules and nanomaterials. He is also co-founder of Aminium Technologies Private Limited. His topic for today's webinar is flow chemistry for the synthesis of organic molecules. Over to you, Dr. Arun Nikam.
Yeah. Can you see my presentation?
No. Ah, yeah, now it is visible.
Yeah.
The slide is visible now.
Yes. Good morning, all of you. So today I am
Yes.
going to talk about flow chemistry for organic chemistry. So before going to that, I would like to introduce my firm, that Newarchem Technology. So we are in offering consultancy services in scalable synthesis of metal oxide, metal nanoparticles for various applications, as well as drug and polymer nanoparticle formulation using microfluidic devices. So apart from that, I have also worked with flow chemistry solution for organic molecules with many industry to develop APIs. And we are expert in design of reactors, flow optimization in fluidic devices, scale up and computer-based flow modeling. So let me begin with like introduction to batch and flow chemistry. If you look at the batch reactor, it is easy for operations. We can optimize nitration reaction, acylation reaction, or many other esterification reaction. The major drawback of this batch reactor is production rate is low, and we have poor control over the reaction parameters that hampers the reproducibility. So if you look at the batch reactors, we optimize a lot of reactions. As conventional flow chemistry, we say that it is better for production, but batch reactor is modular, so we can do a many reactions in single batch reactors. But there are inherent problem that we need to wash the reactors, replace the chemicals, so that take lot of time, so that reduces the productivity also. Hence people started
Sir,
using.
excuse me, sir. Your slides are not getting changed on the main screen. Slides are not getting changed.
Not getting changed.
Ah, now it's okay. Now it's okay. Yeah.
This is okay.
Yes, yes, this is okay.
Okay, then I will share like this.
Okay.
So these batch reactors are easy for operations, as you know. So it is modular. So you can optimize many reaction, nitration, acylation, alkylation, or many of them. Name any, you can optimize in a batch. Major drawback is production rate is low, as well as we have poor control over the reaction parameters that hampers reproducibility and selectivity. In typical batch reactors, we have to add the chemical, remove the products, and wash the like vessels. So that increases your dead time. So dead time is more. So ultimately you reduces the productivity. Hence people started using this continuous stir tank reactor, so which can increase the production rate, but we have limited control over the reaction parameters. So therefore, people have started using tubular continuous flow reactors to achieve great control over the reaction parameters. So in continuous flow reactor, we can control the reaction parameter which cannot be controlled in batch and continuous stir tank reactor, such as reagent addition, product remole rate, mixing, heat and mass transfer. Those we can control using this continuous flow reactor. So we ultimately end up with a reproducible and highly selective process. And it is modular, so we can integrate with automation to run the setup without human interruptions. So we don't require manpower, and it will not have a manual errors of manhandling. So we can avoid that. In this continuous flow reactor, microreactor has greater advantage because of high surface area to volume ratio. As you go to a microreactor, the surface area to volume will increase. Because of
Will
this,
you, sir, excuse me, will you change to this screen show to the full screen?
okay,
Full screen.
can you see
If
now?
we are seeing, but it is only in the slides form. Full screen form, if you switch over, it will be bigger in the size.
I am in the full screen mode.
Okay, okay. Go ahead, sir. Go ahead.
Yeah. So can you see the slide?
Slides we are able to visualize, but they are in the slide. I mean, slide mode only. Full screen, they are not appearing. So
Okay,
all
okay.
everything is looking very small, not in
Let
the
me
enlarged form. Enlarged form.
let me reshare again.
Yeah.
Enter screen. Can you see now?
Mm, better than the earlier. Yeah. Yeah. Yeah.
Okay.
Go ahead. Go ahead, sir.
Okay. As I mentioned, like in continuous flow reactor, microreactor has greater advantage due to its high surface area to volume ratio. So as you can see here, that surface area will increase when you go for microreactors. And we can achieve faster mixing due to smaller diffusional distance. Distance between two mixing reagent is very small in micrometer range, or we can say in millimeter also. And okay, and we can enhance the heat transfers. As you know, exothermic reaction, we need to take out the heat very fast. So to take out the heat, high surface area is more efficient to take out the heat. And we can operate this reactor under safer condition due to smaller hold up volume. So we can handle explosives and hazardous chemical because we have enhanced heat transfer, mass transfer, so that can eventually reduce your risk. And handling the explosions or hazards at small level is you can handle very easily. At large level, you cannot handle. So using this microreactor in microchannel, we can handle low lifetime intermediates like from few microsecond to a few seconds of intermediates which are unstable. If I do not react after certain second, it will decompose or it will form another product. To handle that, we can use a microchannels of microreactors. Due to that, the flow chemistry become important tool in academics and industry. So coming to the next slides, are you able to see my next slide?
Yes, sir.
Uh, Coming to the organic reactions and flow chemistry. From last decade, industry are trying to translate batch organic reactions into flow chemistry to overcome the batch drawbacks. So using flow chemistry, we can address various issues related to organic transformations like exothermic reactions. You can know like nitration, oxidation, hydrogenation, brominations. Multi-phase reaction where mass transfer is important. Unstable intermediate where your mixing is important. And selectivity issue where we have your temperature control, product remole rate is important. Again, mass transfer for oxidation and hydrogenation, which is gas liquid, solid reactions, and heat transfer related reactions like ozonolysis, nitrations, hydrogenation, Grignard reactions, which are highly sensitive to heat. And nonetheless, the safety of our chemical processes is important. So we handling in flow is very easy because we can have small volume we operate. So it is easy to handle these reactors. So then our approach is to use the flow chemistry for reproducible, scalable, and selective synthesis. Then I started in my postdoc to study telescopic continuous flow cyanation using mass cyanide source. Cyanide is an important functional group for natural products, drugs, and various derivatives. So conventionally, it is introduced using potassium cyanide, sodium cyanide, and organic cyanides. As you know, sodium cyanide are very poisonous, and we are not allowed to use it in lab. So we cannot use these poisonous reagents. And these organic cyanide are unstable, most of them at room temperatures. Hence, the question comes in mind, what is an alternative for these cyanide sources? So we found that this bromoxazole as a low toxic and stable mass cyanide source. To introduce cyanide using this compound, as you see, here is a cyanide which is masked. So you cannot recognize this is cyanide. To introduce that, we need to design our synthetic route properly as an organic chemist. So you can see, so we lithiate using butyllithium with this bromine, so it will give lithiated product, and then quench with trimethoxyborate to form this boronic ester. And then we couple with bromobenzene and to make this intermediate of oxazole. And again, with this acetylene group, you cannot see this acetylene group, you can do a retrodiesel reaction to obtain these cyanide compounds. So to begin with, initially, here in this slide, you can see the schematics for flow optimization of lithiation. So how do you know that lithiation is completed in flow? So what we do is, this is M1 mixer M1, this is M2 mixer, where in M1 we inject N-butyllithium and bromoxazole. So where lithium exchange happen here at bromine, and after this methanol quenching, the hydrogen will come here. So here is hydroxazole you can obtain. So similar reaction we did it in batch. So we did in batch at minus 70 degrees Celsius, because in batch we don't have control over the heat or temperature. So we have to do at lower temperatures. As previously Professor mentioned that in batch or a larger reactor we have hot spot. So it is very much chances to decompose our product. But in flow at room temperature, even we do a reaction, so we did not observe any decomposition because of efficient mixing and high heat and mass transfer. So we screen this is typically flow setup look likes, so which is made by us. This is Teflon tubing you can see, and these are the fittings which is from IDEX standard fittings. So this is T mixer, here another T mixers. So in first we inject butyllithium and bromoxazole, and second we inject methanol to quench the lithium to form a uh, hydroxazole rather than bromoxazole. So in batch we get multiple spots, but when we do a flow, we optimize various reaction condition, number of equivalents of butyllithium, reaction temperature, residence time, out of which this is optimized reaction parameter where we get 98% yield for the particular bromoxazole, hydroxazole. So after optimization of this reaction, we want to do a second step, that is borrylation. As I mentioned in my previous slide here, we do a borrylation reaction. For the borrylation, instead of methanol we quench with trimethoxyborate, and we optimize various reaction parameter. at room temperature 6 seconds, we get 88% yield for this borrylation. Then the next step we want to do is coupling reactions. So we do a telescopic coupling reaction. Telescopic means product from previous steps we have taken into the syringe. Here in this syringe we have taken and taken to the next step. So it is not in one flow. So we have break this here and took this product for reagent for the next step. Then so we mix this at M3 that KOH to form a boronic acid. Here we will form boronic acid and then bromobenzene with palladium catalyst under 90 degrees Celsius, 40 psi BPR. We did this reaction to obtain this bromoxazole intermediate. So we did various optimization with solvent combinations equivalent of boronic acid, time, temperatures, and we get 89% yield. So now we did these three steps, two steps in one go and second step in separately. So what we want to ultimately join this part here from here to here. So we want to integrate three steps in one go. So we try to integrate. This is typical schematic where we have butyl lithium here, lithium exchange will happen, then here borylation will happen, then here boronic acid will form, and then here we have coupling reaction under 40 psi BPR. So this is typical setup, look like real setup. So there are many connections. You can see from here, here T mixer, here another T, here another T, here another T's. And at the end, we have back pressure regulator at 40 psi. So we run this reactor for few minutes, but surprisingly, we observe color change into this syringe. You can see here the lightish yellow color, but here is brownish. So we found that there is some difficulty in flow when we integrate multiple steps. So because of uneven flow rate, this pump has different flow rate, these pumps has different flow rates. It may not absorb the back pressure. So that was back mixing happens. Means
Hello.
instead of going solvent reagents straight away, it will come to this syringe. So due to that, we could not do integration of these three steps. Then we decided to go for telescopic approach. So as you saw, we did this separately. We did this separately, and the last step we want to optimize is telescopic approach for retrodiesel reaction, where we use this acetylene dicarboxylate acetylene to do a retrodiesel reactions at 200 degrees Celsius, 100 psi. With lithium, we quench this ester group and we obtain these cyanide compounds. So these cyanide compounds, we have optimized various reaction parameter to vary the flow rate, vary BPRs, THF to toluene ratio, we vary. And we obtain various derivative of cyanides for the cyanation. So what we learn here is multi-step cannot, all the steps cannot be done in flow, but various process can be done as a multi-step into the flow. But in this process, we cannot integrate all the step in one go. So we have break up like first one step, another one step separately, and last one another separately. So and for to maintain the high pressure and high temperature, we need to inject the high boiling solvents to do a reaction at higher boiling point. So we did that and we obtained various cyanide compounds. So coming to the next topic is hazardous to value added products. This is parathenium, which is used as chemical warfare reagents, which is very neurotoxics. As you know, like Russia is also trying to attack chemical attack on Ukraine. This is similar species has been used previously in 1941 to attack the in World War II. So another derivative of parathenium is paraxonum. So which is also chemical warfare reagents and which is produced in large quantity in a military to have chemical attack. But over the period, it will decompose and it will decrease its reactivity. But there is problem comes because we need to dispose these stockpiles of this peroxone over the period, because it will decompose automatically. So we need to dispose efficiently. So conventionally, what people do is do incineration or degradation. Incineration means burn this peroxone, so it can release CO2 or phosphates or nitrous oxide. So that causes the secondary pollution like air pollutions, and which can act as a chemical waste, even though it is non-toxic. But what we want to do is we want to convert this non-toxic chemical into value-added chemicals. So we decided to convert this peroxone into valuable chemicals, so which can generate wealth. So we want to prepare the paracetamol. Using this peroxone, we degrade this, again reduce this, and again acetylation to give a paracetamol, which is tableted drug for painkiller, which is marketed drug in India as well as worldwide. So from the waste or hazardous chemical, we want to make a wealth. So we started with flow optimization to degrade the peroxone using NaOH into paranitrophenol. So which is very simple reaction, but in if you do it in batch, we you observe different observations. The small observations are important because when people do it in batch, it is very small quantity, so they can add into water, so they do not realize that it is insoluble in water. So that causes inefficiency in the batch reactor. When we do it in flow, we dissolve this in acetonitrile, which can miscible with water. So we can do it homogeneously in flow. So in batch, we are getting 70% yield, but when we do it in flow, 3 equivalent NOH and 75°C temperature, we get almost 100% conversion of peroxonone into a paranitrophenol. The next step is then to reduce the nitro group. So sequentially, we want to reduce this nitro group into amino group. So we add sodium dithionate as a selective reducing agent for a nitro compound. And here you can see optimization chart. At 4 equivalent, we get almost 99% conversion for paraminophenol at 120 seconds. So which is very short time reactions. Then further we want to optimize acetylation in continuous. So in previously you remember that we are doing telescopic breaking, but here we are doing in one flow. So where we using HCl, we adjust the pH and add this acetic anhydride for acetylation of NH2 group, so which give a paracetamol. Similarly, we screen various reaction parameters like temperature, residence time, reactor length, everything, and then we obtain like 81% yield of paracetamol. And I hope everything is connecting to me, because this is everybody is using this paracetamol, I think so, for painkiller. So I am telling you recipe of making paracetamol in continuous flow. So after optimization of this reaction in one go, we want to scale up it large scale. For scale up, we use Teflon-based plate microreactor. So you may ask, why do you use Teflon-based plate microreactor? Because it is compact. We did not need to handle complex network of capillary fittings like this. I would say previously I show the capillaries like this wires. So we have compact reactor which is sandwiched between heating plate. So these are the heating plate you can see at the bottom. So we can heat using the electricity. So we can operate this in like low footprint area. So so we degraded up to 28 gram per hours of this peroxone, and we also synthesize this paracetamol in 3 steps up to 5 gram per hour scales. So this is our best achievement in our research work, where we have one flow process which has multiple steps in one flow process, from hazardous chemical to a paracetamol. So, and compact Teflon based plate microreactor decrease the footprint area and avoid the complex network fittings and capillary tubings. I hope like I am in time. So can I go to next topic?
Mm, yeah, yeah. How long it will take, doctor? It will
It
be of.
will take a little bit time. So I will go skip some slide and I go to the end of the presentation.
Okay, doctor.
So like there are various reactors. So this is H cube, you can see, which has inbuilt electrolyzer which can generate hydrogen from water. So we can use that hydrogen for reduction reaction, hydrogenation reaction. So these are the inlets, and here you have catalyst cartridge. So you can fill the catalyst palladium carbon for hydrogenation. And this is vapor tech system. So I have handled this vapor tech system for many reactions. So while while this man is preparing this vapor tech, he has tested in our lab at NCL first for nitration reactions. So I am proud to tell that this is in NCL, they have tested for nitrations. This is Teflon based plate microreactor. So these are the continuous stir tank reactors. Many of you may not know. So we inject the chemicals from top and remove from the bottom. So this is continuous stir tank reactors, and this is stirrer, orate stirrers. And these are the impinging jet reactors where two on anti-solvents and one your main stream goes and precipitate here. So which can be used for sol gel precipitation, nanomaterial synthesis, and this is automated synthesis. So there are many critical challenges in flow chemistry. If you want to know that translation of multi-step synthesis in one flow for large scale production, we need to solve this problem, and handling solid into the flow is important because at smaller dimension the tubings may clog. So you have then again you have to remove that clogging and again do reaction, so which cannot be affordable at automation scale. So hope you understand something from my presentation. Thank you for all. Any questions?
Thank you, doctor.
Yeah.
You have given the information of application of flow chemistry in waste utilization and creation of value added products from hazardous chemicals into the value added products. And paracetamol is one such molecule that you have made from a hazardous waste, and that's really opening a new field for the chemists to dwell into in the days to come. So it's a nice insight you have given to our younger graduates, postgraduates, and researchers to think upon and work upon, so that we can create many more things by adopting these newer technologies, and
Yeah.
make this world a better place to live, devoid of all such hazardous and waste chemicals into utilize value added products. So
Yeah.
nice piece of information you have shared, doctor. And on behalf
Thank
of
you
all
for
the,
opportunity.
it's our pleasure, doctor. We will, explore the possibilities of extending this to our student community in UG and research level in the form of small project work or industrial visits, so that they will get hands-on exposure and experience to understand more crux involved in all these technologies. So we will take up this with you in future in a collaboration manner, and we will work upon, and so that our students will be benefited in their academic pursuit in the days to come.
Yeah.
With this backdrop, we, on behalf of all the organizers, we thank you, doctor, for sparing your valuable time and sharing your knowledge and expertise in this field. We are very much thankful to you, doctor, for this.
Yeah. Thank you. Thank you.
Okay, sir. Now we'll move on to the next session. It is now, after having heard so many things about the flow reactions, how to monitor these flow reactions uh, in when the process is going on. The what kind of instruments or equipments are used to monitor the reactions, the product formation, in between the process, how they can be monitored, and what kind of instruments are used and how they are handled. So some kind of instrumentation involved in this flow chemistry we are going to take up in this session. And we are very fortunate to have a resource person, Dr. Shobha Nagapaya. Madam, have you joined? Okay, welcome to you, madam. Dr. Shobha Nagapaya is a technology application scientist at Mettler Toledo Industry. She is located in Mumbai. Dr. Shobha is a trained organic chemist. She obtained her PhD degree from Institute of Chemical Technology and did postdoctoral at Dow Chemicals. She worked in chemical synthesis and catalysis, R&D in Reliance Industries. Madam has 11 years experience in R&D, and Dr. Shobha is Nagapaya is currently working as technology application scientist in Metallar Toledo. And Madam is she is expert in handling the React IR and React Raman technologies applied in the flow chemistry. Welcome to you, Madam, and now the floor is given to you to give your presentation. Over to you, Madam.
Thank you.
Thank you.
Can you see my slides?
Yeah. Full screen, you can make it.
Yeah. Can you now see it? Am I audible?
Yes, audible, and it is now visible. Slides are visible.
Okay. Okay. So, first of all, thank you very much for giving me and Metla Toledo an opportunity to speak in this fundamentals and applications of flow chemistry webinar, and also to put me in this distinguished list of speakers who have spoken before me on the fundamentals of flow chemistry, how flow is used in the applications, various applications in the API industry, and how flow chemistry is used in simple organic molecule synthesis. So now, having heard about the flow chemistry and the basics of flow chemistry, I would like to now focus a little bit on the analysis of these flow components and how, especially React IR, or for that matter, the IR technology can be used to understand the different components coming out of the flow chemistry reactions. Yeah. So now, presently, as you're aware, the reactions are mostly done. Although we are talking about flow reactions and everything, but most of the companies and most research organizations are still dependent on the round bottom flask and reactor to perform reactions. And we know how difficult it is to sort of go from a lab scale to the plant scale uh, manufacturing. It poses problems in terms of safety. There are some efficiency related issues in terms of the product and yield. And also, when the product comes out, there are some problems in terms of the purity. So, this is how the present scenario is. Although we know flow chemistry is being adopted by many companies, and they are doing wonderful job. But by and large, it will perhaps take few more years for our industry to completely shift from the batch to flow. So how we would see the future where we have the flow reactors, which poses, of course, there will be minimized risk and higher efficiency in the work, as we heard from our speakers before me. And there will be products which you can get on demand. Now, there are advantages of flow reactions as opposed to doing the reaction in a batch. We've already heard it, so I'm going to be a little fast in explaining this. So first of all, there will be more control on what you are doing. So there will be controlled mixing, there will be efficient mixing, and whatever reactions you're doing, there will be precise temperature control, and there will be more understanding of what exactly you are doing. Secondly, as far as the scale up issues are concerned, it will be easier to scale up a reaction which is done on a flow, because you can monitor what's happening at every step of the reaction. And also, whatever reactions you're doing, it has to be it will be made to as a customizable and scalable technique. And there are quite a few reactions which are difficult to do in a batch mode, but it has been observed that when you move from batch to flow, the chemistry becomes more it looks more feasible and easier to understand. And with the inclusion of pad technology, the process analytical tools, you have better understanding of really what's happening in a reaction. Now there are scopes of improvement in every technology. Now in this case, when we move from batch to flow, first of all, it eliminates the need to isolate intermediates, because as we have heard, intermediates can be part of the ongoing process, and they can be made to completely convert into the product formation without having to even isolate or do anything about it. And of course, you can fine tune the chemistry for better yields and reduced impurities. And because of the different flow cells available, because of different flow reactors available, the pumps and the advancement in that field, it's open to performing different kinds of reactions. You can have click reactions, you can have different and difficult reactions, and you can perform them in the flow reactors. Now let's quickly try to understand what all we need to know when we are doing a flow reaction. This is a very simple schematics of how a flow chemistry works. We have A and B, they are mixed. The intermediate C is formed. Then D is dosed to this reaction. There's another round of mixing, and eventually the reaction happens in the reactor and we get the product. This is a very simple way of understanding the reaction. But whenever we do this kind of reaction, we really want to know what is the residence time of these reactants. Are they flowing correctly in the reactor? Are they settling enough to be mixed properly? Is the conversion that we are getting is good? Is it faster conversion? Is it slow conversion? And what kind of stoichiometry are we looking at? Are we looking at 1:1 kind of reaction, or for that matter, what are the reagents that we are using? So these are some of the information that we would like to have when we are doing with this kind of reactions. Now, suppose there's an intermediate which is also getting formed, then we want to know why is it getting formed? Is it a routine reaction? Like, for example, in many reactions we have seen there's an anion generated. There are reactions where some other kind of intermediates are forming. Now, the question is, when they are getting formed, do we have a third reagent for it to react so that they can give the product smoothly with the proper conversion? Is the intermediate which is getting formed, are we able to detect it? So you see, there are these information that we would like to have. And of course, once we dose the third component here, D, then we would like to know whether sufficient amount of D is getting added so that you get the exact yield of the product and the perfect conversion with better purity. So are we in a position to decide all this? And once the product is formed, how do we know we got the product? Is the steady state achieved? Do we have the optimum flow rate in the reaction? And is the yield good? And whatever product we are getting, is it on demand? So these are some of the information, some that we would like to have when we are doing a reaction. Now there are quite a few challenges, which is that once you have a flow reactor and there is input and there is output. Now the only way, like in case of batch reaction, what do you normally do? You take out the sample, you get it analyzed on HPLC or GC. These techniques, you simple method of doing in a lab is just to run TLC and see whether your product is being formed or not. Now, there are other issues while doing this kind of online analysis. For example, you won't be able to detect the intermediates because, as you know, they have a transient phase and they will not be detected in any of these techniques. And also, if you are dealing with some toxic material, although it is in very small quantity running in the flow, you don't know whether that can be monitored in the known analytical devices. And there are different challenges, like in case of a flow there can be dispersion issue, there can be diffusion issue. So are we in a position uh, to understand the reaction while the reaction is going on? So normally we take the sample out and we give, like I said, we do offline analysis. Then there are these inline UV detection also available. There are many labs which are using it. But again, with UV, the problem is that you have to see it at a particular wavelength, and if the proper mixing is not there, you are going to see everything comprehensively, and you will not be able to see each product separately. So there is this inline spectroscopy, FTIR and Raman. So these can be used, which give the real time information of what's happening in the reaction. And this is this is made possible while you are doing the reaction. Like, you don't have to take out the samples while the flow chemistry is going on. You will be the flow cell is connected, it is attached to the outlet of the flow cell, and as and when the reaction is going on, you will be able to instantaneously see it on your screen. And if you want to tweak some conditions, you can do it in situ as the reaction is progressing. It provides structural and mechanistic information about the reaction, and we can also do the real-time optimization of the processes. If at all you feel that the temperature is not sufficient, you need to stoichiometrically the two components are not matching, you need to add more of it. You can do all that while the reaction is going on. Now, this is, like I said, you can monitor in situ under actual reaction conditions, and most importantly, there won't be any interference from bubbles and solids while mixing. There is selective information on the liquid phase, and you will be in a position to understand and focus on the exact reaction parameters. So this is the instrument. Flow cell is connected to it. So instead of so you have this inlet which is attached to the flow cell. The outlet can either go back to the reactor, or it can go to the effluent stream. And as and when the reaction component touches the flow cell, you get the movie of the reaction that you're doing. I'll tell you how exactly it works. Before that, this is our React IR with the probe. So we have probe. It's actually probe-based technology, and we do have flow cell. We have continuous data collection. There is a RTD sensor, which is resistance temperature detector, at the tip of the probe and in the flow cell. So while the reaction is going on, you will be able to monitor the temperature as well. And it comes with the software ICIR. So with just one click reaction profiling, you will be able to see the reaction right in front of you, what is getting consumed, what is getting formed, and whether there is any intermediate forming, how many side products are forming. So all this information you will be able to get once the reaction starts and you connect the flow cell. Now, for example, this is a very small snapshot of one of the reactions uh, that we have done, and I've tried to show here. So this is a simple anhydride to the ester formation. So where initially, if you just focus on this on the spectra, uh, you can see that the pink line is depicting the anhydride peak, which is slowly decreasing over time because there is a new peak of carboxylic acid which is forming with respect to time. So this is a technique where you get the concentration changes, you get to see the changes in the molecule with respect to time, and that is why you can actually understand the kinetic behavior. You should also be able to understand the mechanism of the reaction. Like in this case, how the progress of anhydride to carboxylic acid is taking place. we are able to profile it over time. On the right hand side, you have this height or the concentration versus time. So this orange line indicates that the acid is forming, and the blue line indicates that the anhydride is decreasing over the period of time. So if you just follow it, you know when to stop the reaction, how much of the consumption has taken place, so you can immediately read out your reaction. Now, what is it based on? This is based on the attenuated total reflectance ATR sensor at the tip of the probe. Now, you will ask, what is the difference between the standard FTIR and what you're talking about? So, when we have the standard FTIR technique, this is also FTIR, but what we have as a standalone instrument gives you the data of that time. You take the sample, you take the FTIR spectra, and that's about it. Here, you put the probe, as in the sensor, in the reaction mixture, or you connect it to the flow cell if you're doing the reaction of flow chemistry. As and when the reaction is going on, it is going to give you the changes in absorbance, which is concentration, with respect to time. So it's basically, it works on this ATR. We have this ATR sensor. So when IR radiations fall on the tip of the probe or the flow cell, there'll be reflections, and depending on the dipole moment change of the molecule, some molecules will absorb these IR radiations, and that is what is detected by the detector. And it follows Lambert-Bayer's law, which is absorbance is equal to small a, small b, small c, where small a and small b are the absorptivity and optical path length respectively, and both of them are constant for any given system. So absorbance is therefore directly proportional to concentration. So whenever you are taking the FIR, it gives you the absorbance, and by Lambert-Bayer's law, we know absorbance is directly proportional to concentration. So you should be able to track the concentration with respect to time. Now, exactly how it works. So whenever you take an IR, you have absorbance versus wave number. So you collect the data over time. So every few seconds the data is getting collected. Now whatever change is happening in the reaction stream, for example, in the previous example we saw anhydride is getting converted to an acidic group. So whatever is changing, you will see the change in the peak. You profile that peak which is changing with respect to time, and this whole profile is getting it gets converted to absorbance versus time, which is nothing but kinetics. And you have this green line, which is the consumption of reactant A, blue line, which is the formation of the product. And if there is an intermediate, you can see it because you're not removing any sample from the reaction, and all this is done while your reaction is on. Let me give you a very small example how you can understand it better. So this blue line that you see on the top of the slide is the spectra of water, and you keep on adding sugar molecules to it, and you see those small peaks coming because of the presence of sugar in water. So we are going to take that one peak, profile it, and this is how we get the trend, which is that till about ninth minute I have not added anything, so there is no sugar in water. You add some more component of sugar, it the concentration increases, it reaches a plateau, and then you add some more, it reaches a plateau. So we get this systematic addition of the component in this particular solvent. And this, because it also has a detector, so we are able to see that it's an endothermic reaction. So not only it's a qualitative tool, but we also get quantitative assessment of what's happening. Now this will work for any system where the components involved are IR active, B, the component of interest is in solution, and the concentration ranges are greater than 0.1%. In all this situation and in all this condition, React IR will work for you. Now we have the ICIR and IC Raman software, which works on this one-click analytics. Basically, it's quite intuitive. So so you have the instrument connected to the laptop, and whatever changes are happening in your flow reaction, whatever information the system is gathering, you will be able to see it on the software. And it gives you it gives you the absorbance versus time, which is concentration versus time profile. It gives you the best peak to profile for any of the component, and it also inherently builds a model which tells you what it should be the progress of the reaction, like what you generally do on an Excel sheet post reaction of finding out the rate of reaction and all. At least that concentration you will be able to get immediately while you are doing the reaction. And believe me, everything in less than 2 minutes, because we have this option of taking samples every second, every 2 seconds, every 30 seconds. If the reaction is very slow, then of course you can increase the time limit. But every few seconds a sample is taken, you start seeing how the sample behaves in the reaction. And it also gives you possible functional group which are there in your system. So this gives you an understanding what functional group is changing to which functional group. So that kind of possible presence of a functional group, that detail also you will get. Now we have for a successful reaction monitoring for in React IR, we have this IR which is in the fingerprint region, because that's the region where most functional groups in the organic chemistry give you the information. Then we have the probes and the cell, and the software is the heart of the system, which basically tells you what exactly happening in the system. Now let's take few examples. Now this example is of ozonolysis, where styrene molecule in the presence of ozone gives you this aldehyde. Now, this example is actually a published data from one of our customers. It's also there in the journal for you to read. Now, the challenge in this reaction was that there was a time frame in which the 2 kg of the product was to be formed. There was not much information which was available beforehand for them to make the product, and the pilot plant was not available. So the only thing that they had was the reactor and the ozone generator. So what they did is, as you can see, the styrene is pumped from the top. You have ozone generator pumping ozone from the bottom, and there's a bubble column in which our probe was inserted. So instead of probe, it could have been the flow cell. But because it's a live example done in a continuous manner, so I've taken this example to illustrate how we got the information. And once the ozonoid was formed, we got that information on the screen, how the ozonoid is getting formed. It was immediately diverted to the quenching solution where the products were isolated. And the whole process was optimized within a very small, within a very short time. And they were able to produce 1.4 kg of the product a week, and the product quality was more than 98%. Because as you can see, you have an online technique within the reactor, and as and when you're doing the reaction, you're able to see those changes. So you don't have to take any offline sample and then optimize. So those things are completely eliminated. This is an example of controlled accuracy, where the two reactants are taken, and two flow cells were also taken. So one was to understand a particular peak, the other was to understand another peak. And here the most important thing was that some of the aggressive materials were used, like in this case azides. They didn't want to use an excess of azide. So with the flow chemistry they were able to understand how much of the azide is to be formed, when they need to add the third component for the reaction to proceed. And they were able to substantially reduce the quantity of the azide. So this was of course made possible because they used flow chemistry to do this reaction instead of a batch mode, which would have been anyway difficult. And optimization while doing the reaction was made possible because we had our tool in between the flow cell. Now this is an example where a vapor tech system and our flow cell was it was connected to vapor tech system, and fluorination reaction was done. So React IR was inserted after we have the calcium carbonate and the silicon oxide column, and we got the product. Now interesting thing here is that the time for the product to come out of the reaction was about roughly 20 minutes, while the actual product actually came out in 36 minutes. So there was a little bit of prediction as to how you can get the product, and then uh, the additional time required for the formation was also sort of understood because of the dispersion and the diffusion issues. But the thing is, this was all done online. So if at all there is any issue, you can immediately stop the reaction, you can make changes, and you can see what's happening to the reaction scheme. Now this is an example where A and B again connected to the IR or UV, and in the current situation, the use of IR was to generate the dispersion curve where they were able to see the reaction. But if you have this React IR probe, you can actually use real-time concentration of a product-specific band from React IR, and you will be able to convert the flow rate, which is coming from the flow chemistry. Then the third stream could be incorporated in it, and you can see how the product is generated. So all this is completely automated. You can like I said, you can make changes to the system while the reaction is going on, and you can observe both in terms of there is no need for any visual change observation. You can actually make do with the changes that you are able to see on the screen through our React IR flow cell. Now, this is an example of the synthesis of pyrazole, where when there was no React IR control was used, then about 10 equivalents of the toxic hydrazine was used. Virtual observation was done to understand when you can allow the hydrazine, other molecules to sort of come in contact with the reaction stream and give the product, and extensive purification was required. But with React IR control, they were able to understand how A and B are reacting. Are they forming any intermediate, or are they forming some sort of a product? And when the hydrazine has to be added. So all that information was gathered while the reaction was going on. It reduced the reaction temperature. It reduced the formation of side products because there was no excess uh, uh, excess dosing of the hydrazine in this case, and they were able to get the crystalline material from both these processes. So I would like to summarize that you can actually monitor chemistry in situ under actual reaction conditions. It can be you can have toxic reagents, you can have hazardous reagents, but then this can be done at all these conditions without having to take out any samples for analysis. You can online you can get the concentration changes, so it's not just a qualitative tool, it's a quantitative tool. So you can track the concentration changes of all the reaction components involved, and you can eventually find out what is the yield and the percentage conversion. Therefore it eliminates the time delay associated with offline analytical methods. And we have a very strong software by which you can actually understand the whole progress of the reaction, and you can optimize chemistry which are done in flow cell and flow chemistry. Yeah, thank you.
Thank you, madam. We are seeing a lot of.
Hello.
Thank you. Hello. Am I audible?
Hello.
Hello.
Yes.
Yeah. Thank you, madam. Lot of complimentary messages are coming in the chat box about your session, and really you have exposed our faculties, researchers, and students to a new field wherein you can monitor the reaction process, how it is happening, and where the controls can be made by using your tools. Really, it is many of the chemists, students, as well as faculties to use such kind of facilities so that the reactions can be improved and we can get the products in a better manner. So, excellent session is given by Dr. Shobha. And on behalf of the organizers we extend a very heartfelt thanks to you, madam, for sparing your valuable time and cooperating with us during this process of organizing this webinar. We have been in contact since long time, and dates were finalized, and ultimately we have had this webinar today, and you have presented your nice presentation, doctor, and thank you very much, madam. Thank you very much.
Thank you so much.
Thank you. Now we move on to the last session of this webinar, and we have taken the liberty of making our own alumni stay till the end of this webinar. Is Dr. Ashwardhan Malpani have you joined? Dr. Ash?
Yes, sir, I have joined.
Yeah, welcome
Yeah.
to you, Dr. Ash. We have been kept waiting, and we have taken your session last, and we are very proud to have you on this webinar. And you are the man who has given some certain kind of leads to us to organize this webinar, and through your lead, through your help, assistance, we could get the eminent faculties for this webinar. And really our institution, Bangur College, is always remembers you for your achievement, what you have made in your career, and you are the motivation to our many of our students. And we are very happy to see you on this platform from an international arena from South Korea. Really, we are all very much proud of you, Dr. Ash. And before we move on to the session, I would like to give a brief introduction of about our own student, and who has excelled in his field, international arena. And at this juncture, we must remember Dr. Khazi, the professor of Karnataka University, Dharwad, who is instrumental in sending Ash to Korea and making him to pursue his PhD studies in Korea. And unfortunately, Dr. Kazi is not with us, but his blessings are there with all of us. So, Dr. Ashwardhan Malpani completed his Doctor of Philosophy in Medicinal and Pharmaceutical Chemistry under the guidance of Professor Jang, University of Science and Technology, South Korea. During his PhD, he worked on discovery and development of novel small molecules as antiviral agents against the pi coronaviruses, influenza viruses. The work against pi coronavirus was successfully licensed out to Novartis in the year 2014. During his PhD, he also worked on stimulus responsive azobenzene supramolecules, which were successfully developed as materials for reversible image printing and as molecular actuators. After his PhD, he worked as postdoctoral fellow, followed by a 2-year contractual tenure of senior research scientist at KRICT Daejeon, South Korea. During this period, he continued working on development of novel antiviral agents together with organic method development utilizing visible light photoredox catalysis. Presently, Dr. Malpani is working as manager, new technology development, synthesis division, research center, Daewoo Bio Incorporation, South Korea. Daewoo is one of the top 5 pharmaceutical groups in South Korea. His present work is in the field of development of novel processes for bulk drug API utilizing advanced techniques. In this regard, he has been working on enzyme-mediated process and flow process for important APIs. And Dr. Ash has published more than 15 papers in high-impact journals. And today's he is presenting his talk on scaling up in flow process. And at this point, I must tell, Yash is having some health issues. In spite of it, he has been continuously helping us in making this webinar as a reality. And for having done all of, for doing all this, we from all our institution and all organizers are really, really thankful to you, Ash. And please, over to you, and you can do your presentation.
Yeah, thank you, sir. Thank you for such a nice introduction of me. I don't know I deserve that much or not, but thank you very much. And Before I start, I would like to first thank all the hosting team and organizing committee, Dr. Shobha Sharma. Whether I used to call her like Shobha ma'am, so she's very close to me. Then Professor Hasmani, Professor Amin Bhavi, Merwari sir, and our distinguished speakers, all of them. They have spoke such a nice content here today that I feel like very much shy. What should I present now? But anyways, I had been working on like basic research for a long time and was introduced to flow chemistry just 3 years back. And as you all have heard today, it is so interesting, and that's how it made me also so interesting. And I thank Devum for giving me opportunity to work on this advanced field and learn more about it. So basically today what I'm presenting is about how to scale up in flow chemistry. But my content is, because I understood that the audience is beginner in flow chemistry, most of them. So I had narrowed down my topics to some kind of a small introduction required for the scaling up, and then I will take my own work example, which we have published in Journal of Flow Chemistry, and show you how we have carried out the scaling up of our process here. So once again, I thank you all of the speakers and also the hosting committee before starting my presentation. So let me share my slide here first. So is it visible now to see the slides? Am I audible to everybody?
You
Hello?
are audible. You are audible.
Yeah, and my slides are visible?
No, no, they are not yet shared.
Not yet?
Not yet, yeah.
Um, Abhishek, can you check out if it is some issue in sharing? Because here it's showing sharing.
Abhishek? Yeah. Yes.
So, Abhishek, is it visible to all my slides?
Now they are visible.
Yeah.
Slides
Okay.
are visible.
So, as I told, my initial content will be basic flow chemistry topic related more or less related to how we do scaling up during a flow process, and that too I have not gone very deep and not too vast, just like contents which are easily understandable, and then I will take my example here, which we have done in our own company. So I will not talk much deep about flow chemistry, as we have heard so nicely from Ma'am Dr. Karuna, and also other speakers who have spoke in specific topics. So in general, we know that now the flow process is nothing but where reagents are pumped and the substrates are pumped through a continuous flowing stream, and they meet in a designated reactor zone where the temperature and the architecture of that zone is made in specific to certain type of reactions, and then the output is collected in the form of pure or crude product. So this is generally a small, we can call a flow process where which we can explain to anybody in brief. But we have been doing this scale up from long, and my topic is how to scale up, right? So scaling up in batch process is always is well known to everybody. But what are the issues related to the scaling of batch process? We rarely consider when we are at lab scale, but when we go in bulk production, this creates a lot of issues, and it has to be considered very nicely. Otherwise, we may end up in getting loss of product or huge losses in money. So what happens in a batch reactor? If you can see here two diagrams at the top, the diagram shows that a simulation of NaCl and NaOH quenching, HCl and NaOH quenching. In the first diagram, we have seen here the how concentration changes in a reactor, in a batch reactor through stirring. And you can see the blue zone are the diluted portions and the red zone are the concentrated areas of reagent. Then the second diagram shows how the temperature is or heat transfer is taking place in a batch reactor. So you can see here where the stirrer is there the more or less uniformity is more, but as we go at the top of the reactor, there is less uniformity and less heat transfer. So what happens when this kind of issue reactors are used? So when we are talking about batch process, in a batch process, this is a general example of a process where the C is a impurity generation and a B is the desired product generation. So when we apply heat, because there is no uniformity of heat here, what happens? We have to apply excess heat to make all the molecules of the reaction to achieve the activated state, and in that way we end up applying more heat because of non-uniformity of the heat transfer, and then this results in the formation of impurity C also together with the desired product B. Now, when we talk about flow process, what happens when the heat and mass transfer is so such a nicely happening that we don't need to apply such a vast range of heat. We can even just apply the specific required heat, which carry out the desired reaction only, and no side product is generated. So this is one of the drawback. We end up in side product formation, and sometimes because of this non-uniformity, longer than expected duration of reaction times happens. Then second, the third problem is safety issues. When we carry out reaction in batch, as already explained by other speakers, that we end up in having sometimes runaway reactions, and then like accidents in batch processes, and also in cases where we use or generate hazardous substances in batch process, so they have to go out or leave the system or consumed in the system, but they are in such a large amount that it's not easy to handle them or control them, and that's how it can end up in infecting or causing damage to life and other things. Then another issue with batch is when we go up on from small scale to a larger scale, the reproducibility of result doesn't happen so nicely in all the cases. So that may be the reason, because of, as I mentioned, inefficient mixing or heat transfer, or sometimes because of the change in the starting material specification. So if that happens, what happens is one batch might be of worth maybe 1 crore or maybe of 10 lakhs. So that whole money get wasted in one shot. So if we carry out this process in flow, then probably we can end up saving that loss. So where we should consider to scale up flow, or where the flow process will be always better than batch, or do the batch processes are always bad to carry out? So my answer is batch processes are not always bad, and flow processes are always not good. It depends on each chemistry and also the purpose of doing that chemistry. If the purpose is to do like faster and with less cost, probably sometimes batch is also better than flow, but flow is definitely better in some cases. For example, in photochemistry or visible light photoredox chemistry, we know that in scaling up of this type of reaction, it has inherent drawback. The inherent drawback is as we increase the thickness of medium and pass light from an outside source, as the thickness of medium increases, the transmittance of light reduces drastically or exponentially, and that's how we don't end up getting same result in as we used to get in small scale, because there we use smaller or thinner apparatus compared to large scale. And secondly, if we increase the concentration also, you can see that also results in this diagram. You can see that it again results in decrease in transmission, and that again will affect the outcome of our reaction. So that's the important thing here, that if we want to carry out large scale photo redox chemistry or photochemistries, then it will be always better to carry out in flow if it is possible. And then secondly, other chemistries where we use microwave or sonication, We cannot do a microwave radiation of a 10-ton reactor or 10 metric ton reactor or a 5 metric ton reactor. Even sonication is not so easy, though there is possibility, but and there are instruments like that, but it's always not easy to carry out and not possible at all the places. So in such cases, definitely we can have a flow process where we can do a short, as you have seen in Dr. Karuna's presentation. She explained about small agitated reactors. So these kind of things can be carried out easily in flow processes at many places. So next is electrochemical reactions. So as we know, electrochemical reactions, there's a huge amount of electrolytes required. They are inefficient if the thickness of the cell is big, and I mean it's large. And same like as in photoredox, it has a lot of issues if the scale up is done on electrochemical cells. Precipitation is also a big issue. So these all things can be avoided if it is done in flow chemistry. And as already known, like solid supported chemistry, if we have a solid support where we have to isolate the product and solid support after the reaction, we can easily carry out in flow process by just passing through the column of the solid support. So that is always better. That may be having enzyme supported, which is biocatalyzed, and as mentioned by Professor Dr. Karuna, that biocatalyze is because of enzyme or something related to bio catalyst. So that happens when those are generally costlier and difficult to difficult to obtain, and reusability is required all the time, most of the time. So that's why this is better to do it in flow. Now one more thing which is I mentioned earlier also, like exclusivity. In flow we can carry out some reaction which cannot be carried out at batch easily, or maybe not possible at all. So for example, some reaction which has to be carried out at in DCM at 150 or 130 or 100 temperature, we cannot easily carry out it in batch process because of the pressure constraint. But in flow it can be easily done. And as mentioned earlier also, by the Arrhenius equation, if we can increase in general for any reaction, if we increase the temperature, the reaction rate can increase drastically, and thus we can end up reducing the reaction time uh, in a drastic way. Now, how we can carry out scale up in flow? So in batch you carry out by changing the apparatus from like small RB to bigger RB to then pilot scale apparatus, then to the production unit. But in case of flow, there are mainly three ways to scale up. First is scaling out. What is scaling out? It's nothing but carrying out the process for as long as you want to get the product. So this is the most easiest process, because once you develop the process, you use the same instrument, same method, same setup, and everything is same. Just you keep on checking the quality of the product continuously coming out from the output, and that's how you can scale up as much as you want. But that has some limitation also. So in other cases where it cannot be used, then we go for other method of scaling up, which is numbering up. Numbering up is nothing but you develop a flow process on a smaller or a medium size of reactor and setup. Then if you want to do it in further larger scale, you produce the same setup with another time, and you can reproduce those setups number of times, and then you can then increase the scale of the process. Then third is scaling up. This is actually this is the place where actually the flow chemistry knowledge is useful, if deep knowledge is useful, because whenever you go for a scale up, it's not easy if you do it in same way as you have done it in small scale flow process. So when you do in larger apparatus, similar apparatus but larger in their dimensions, then lot of knowledge regarding flow diagrams, calculations regarding flow diagrams, and then simulations will be required to know before carrying out the process. And also uh, heat and mass transfer also changes a lot which that's why we require the simulation. And you can see here the table, for example, from RB to small RB to big RB, the change is not so great. But if you change in only 0.1 mm diameter to 2 mm diameter, the surface to volume ratio changes a lot, which results in different in heat and mass transfer efficacies. So these are three ways how we can scale up in flow. Then another thing important while scaling up is the telescoping the reaction. So when we do a flow process, generally all the process for any product will not be a single step process. It will be having multi steps in it, and those multi steps may be connected, maybe possibly we can connect them as such directly after as we have seen in batch, but most of the time that will not be the case. And in that case we need to do different studies, and we have to find the solution to carry out this process telescopy in a telescope manner. So for example, we need to carry out we have to think about how we can avoid the workup in certain stages where it is there, and then how we can go ahead even without isolating an intermediate which is generally isolated in a batch process. Then sometimes we need to consider about the solvents, because in the one step we are using some solvent which cannot be used in the second step, so we need to avoid the use of that particular solvent, or we need to find a way to get rid of that solvent. Then again, the impurity formation. So in any process generally there will be a formation of impurities, so how we can avoid it in a general flow process, and if we cannot avoid, how it can be finally taken out from the product at the end of the process. So these all consideration has to be done, including the solid formation, which is one of the most important problem in a flow chemist for a flow chemist, to avoid solid formation of solid formation and coagulate or blocking the flow setup. So I have put here a very good example of ciprofloxacin hydrochloride flow process, which is telescoped and uh, reduced to just 9 minutes of residence time. Now, in this case, they have mentioned a lot of things in this paper which could be understood when we read it. But important thing is there here the formation of N-methyl-diamine. You can see if we cannot take out from the reaction, then in this step we cannot carry out the amination through using this cyclopropylamine. So how to avoid that is done by once we do that, then the formation of dimethylamine has to be removed, because the further step have problem if this is present. So how it has been done is it was converted into dimethylacetamide, and that dimethylacetamide is further finally isolated from the crude product obtained at the end. So that's how we have to think a lot of things when we do scaling up in flow chemistry. Now, why we need to do flow process after all is because sometimes uh, production of some certain chemical is in such a huge volume that if every time we do a batch process, it results in a lot of labor requirement, and overall the process becomes so laborious to do it in batch scale. But if we can have a flow process for it, then once we keep on putting the starting materials to the feed, and then we can keep on getting the product continuously whole all around the year, or maybe for a longer time. Then again, chemical hazards and safety I already mentioned. In flow process we can handle certain chemicals as mentioned in earlier presentation by Arun, that cyanide, and also like azides, and and there are many more which can be handled conveniently in flow process. Then especially in case of nanomaterials and materials related to uh, solar cell or material chemistry, the purity of product is highly important. Especially in pharma also it is very important. So in those areas we need to have a highly reproducible results, and as mentioned in flow we can get it more easier compared to batch processes. Then yeah, so uh, that's the next thing I want to say is whenever we do a scaling up, what all we need to consider is the choice of process and consideration about that I already talked about. But what instrument will be used is also a very important thing here. Which type of pump we will be using? There are various pumps available. I have not listed out everything, but I have listed out which I can remember. And then if you talk about which kind of tubing or the material of tubing should be used, it has to be considered nicely. For example, if we say if we're going for a high pressure flow reaction, then we have to consider not only the internal diameter but also the outer diameter, so that the process can be done continuously for a longer period of time. Otherwise, it may result in leakage or kind of bursting of the tubes, which can cause accidents too. So then sometimes design of the apparatus, like if you have seen fittings in flow, some have flat bottom fittings, and fitting is the end part where we connect the tubings with our any instrument. So whether it should be flat bottom, whether it should be cone fitting, it has to be considered well, how much pressure we gonna give to the flow setup. So those all consideration are always very important when you keep thinking of scaling up, because as you scale up, the pressure and uh, other things also changes in the other parameters also need to be changed, and that's how this consideration always to be kept in mind before going to a further scale up process setup. Then again, the reactors are the important part of choosing a flow process. The reactor can be of different type. Which reactor will fit to my flow process in smaller scale? Probably not be the case in the larger scale. There are cases like that. So we have to think, and also like after the completion of the setup, we use sometimes back pressure regulator. So which type it should be static or variable. Then we have to think about whether we need to connect inline separator, or we have to do separation after the process is complete. Those all consideration requires the particular instrument to be used for the scaling up. Now, there are commercial options also available when we talk about reactor. In case of coding, you can see that a smaller volume, which is 2.7 ml reactor, is also available. And they say that the same results can be reproduced exactly similarly in the larger reactor, which is G3, with a 60 ml of reactor volume. Sorry. So these are commercial options also available, and in some cases you can also go for scale up services where we can, like Thales Nano and Chemtrix, even have the options. You can give them the process, they can give the options how to scale up with on contract research basis. So these are the options how we can go, and these are the basic thing which I wanted to talk about the scaling up. Now I will come to the process which we have carried out in here. So as I mentioned that not all the time we require the commercial apparatus available in the market to be used for scaling up. We can even design them at our place as per our need. And there are also modular arrangements for like carrying out different types of reactions available right now for scale ups. So we can even directly employ them. So in our case, we started with the ILR reactor, and then we changed to a semi-customized pack-bagged reactor, which was assembled with different purchased apparatus. And then finally, we completely created a customized PBR for our process through our collaboration with other designer and manufacturer. So initially the feasibility and optimization done here, then we carry out the scale up to gram levels, and then finally here we could carry out in kilograms scales. Now the process which we carried out here is very simple. It's a single step process. We did the radical hydrogenation of 7-oxo LCA, which is also called as HKCA, and this process requires ready nickel to be placed in a pack bagged reactor, and the substrate is fed as a solution of IPA together with other reagents KOH and tertiary peroxide through the packed bag reactor, generating the desired product and other impurities. So initial screening, which when we did, which carried out, we checked if we can use better catalyst instead of actually this process of random nickel we didn't start at the beginning. We were doing some other processes, but through our initial screening, we came out to know that random nickel and palladium hydroxide are the two catalysts which can give a very high conversion of our desired product with less formation of undesired CDCA. And then the ratio is also important. The more ratio, the better is our yield. So this CDCA is the starting material for this 7-oxo LCA. So we want to be as low as possible because we again add up to get the same starting material. And so we choose random nickel because palladium hydroxide was costlier, and in scale-up cases, random nickel was easily to source compared to a large volume of palladium hydroxide. So when we choose a random nickel, we first obtained it from different sources and checked it. They give little bit of variation in the results, but interestingly, when we came to know that the presence of molybdenum in our catalyst gives specifically 3 to 3% better conversion compared to non-molybdenum containing catalyst. And this we reason out because this may be because of activation of carbonyl group through molybdenum. Then another point was here the formation of side product iso-UDCA. So as all the random nickel catalysts are amalgamated with aluminium, so this aluminium is also known, the aluminum oxide is known to carry out the opener oxidation of hydroxyl group. So we expect that in our starting material or in the product, this opener oxidation takes place because of the presence of this aluminium in the aluminum oxide form, and thus resulting in the formation of keto product, which finally again get reduced to the process similar to 7 keto product and generating iso-UDCA side product. So how did we carry it out the scaling up? In fact, we carried out our scaling up very simply by simple calculation of residence time and catalytic stoichiometry maintained as per the need. So initially we maintained the catalytic stoichiometry to 10 times of the feed, but as you know that as we scale up the even in flow there may not be a so efficient mixing or heterogeneous reactions possibility, so we increased it later on to 20 times because of need of because the outcome was a little bit not matching to our design specification. And for this residence time, we just calculated the total volume of our reactors. We have carried out different sizes of our packed bag reactor, and then calculating the total volume and removing the catalyst volume and the hydrogen volume from it, we can carry out we can calculate the total volume of feed going through per minute, and then we can divide it by flow rate to get the residence time. So when we again went for the final our production scale or process validation scale uh, uh, instrument process optimization, where there also we maintained the catalyst ratio as well as the residence time increased a little bit more to get the desired product. So this was not like so smooth the transformation from small scale to larger scale directly as such, but we need to carry out some trials at each steps. But it was still possible to carry out in our case with the calculation of residence and stoichiometries. Uh, but even as I said earlier, the scaling up always will not be so easy, and it caused some issues here in our case too. We were getting because of the product which is having like almost 350 or 400 daltons as molecular weight. So product used to get precipitated even with zero point 0.1 gram per ml of concentration. So that used to clog our reactor, the reactor which is used to store the solution. Then also that also used to clog the filter which we use before the peg bed column to remove any undesired impurities. And also you can see here, even at the top of the peg bed reactor, we can see some solid formation. So this resulted in development of huge pressure, and we are dealing with hydrogen, so it was very important to maintain the pressure within desired limits. So every now and then we need to stop the process and remove the coagulation and carry out further. The second problem we faced was the catalytic deactivation over the period of use. So as you can see here, the percentage of product keep on decreasing, and also remaining starting material was keep on increasing with time. As you can see here, this is the starting material increasing. So these two problems needed to be solved. So how we solved the first problem was, we tried to change the filter first. So from the earlier 1 micrometer the filter, we change it to 0.45 micrometer filter, and then again together with this we diluted our feed solution from zero point 0.1 gram to 0.085 gram per ml. So this reduced a lot of coagulation in taking place at the time it used to take the coagulation. Then also again with larger use, it used to get coagulate, where we check on pressure, and then as the pressure increased more than 18 bar, which was our limit, we used to again stop the process and carried out intermittent washing. For the catalytic deactivation, um, what we could do maximum is we can do the intermittent washing with KOH solution of IPA and water, and thereby we can remove some of the deactivated catalyst, and thus we can improve catalyst reuse from once to 3 times only. But we are still working on improving its reuse and increasing its ton number, so that we can have a more robust process. Then overall, we could carry out a successful pilot study with 10 kg and 50 kg and 155 kg of batches. Generally, we got call lots in flow process. So 10 kg lot, 50 kg lot, and 155 kg lot, where we can get the desired selectivity. But the problem was here, I mentioned that iso-UDCA formation. So we understood the issue, and we solve that by again removing the aluminum oxide by pre-washing the catalyst before use. So when we pre-wash the catalyst with KOH, all the alumina in its oxidized form can be removed, and that process can be carried out without any problem. And finally, after carrying out the pilot study, we carried out 3 process validation batches, and we did get the desired purity of the final product at the end, with the satisfactory yields, and with the production rate of 4 kgs per hour. This is quite satisfactory compared to what we are doing here in batches still. So uh, overall, I would like to sum up now my presentation by telling this, that FDA is continuously focusing and stressing on incorporation of flow process in drug development, and also providing the guidelines. Even ICH guidelines Q13 is also related to continuous process. Now these are important thing in case of bulk production of drugs or chemicals, because uh, here the regulations make it easier to means the flow chemistry can make it easier to clear the regulation compared to batch in some cases. For example, if we can have in-process control instrument like FTIR, NMR, which is flow NMR, flow IR, flow NMR, and other analytical tools, we can keep on we can supply the robust data continuously to any regulatory agencies. Then we can carry it out for process intensification. We can solve out JP issues, because not many people will be involved, or no intermediate handling of or human handling will be required most of the time. So we can solve the JP issues and other irregularities or deviations in the process taking place by manual errors. Then calibration and then we can just need to do the calibration of instruments continuously to provide all the robust data to these authorities. And one more important thing I would like to say is here we can carry it out the design of experiment and QBT quality by design more easily compared to batch process even in lab scale, but it is also possible to carry out this process these steps in final production site also, which is not easy because of their cost in batch process. So thank you very much to all of you for giving me this opportunity and for your patience listening. Thank you. So I would be happy to answer any question.
Any questions? This field itself is very new, and there may be no much questions. Madam would like to say a few words.
I'm just watching at my best student. Yeah, in spite of his bad health, also he has come to give the lecture. That itself shows his attachment towards the college. We can say that he is the great alumni of our college. And the entire session, today's marathon session, it was started at 10 a.m. So I want to thank Dr. Merwade, his initiative. Even though he is retired from the college, still he wants to give back to the college, and he has taken all this trouble personally. And really, it was a wonderful session. It is a good beginning, and I hope that in future a lot of things will come up, and we'll have more students like Yash flowing in flow chemistry.
Thank you, madam.
Thank you, ma'am.
Yes, you would like to add anything? Yes.
Yeah. So yes, yeah. I'm always there for anybody who need any help or suggestions for any type of their career advice or related to flow chemistry to all the students of our BNDC. It was really great to get attached to BNDC after almost a decade. So, I couldn't get the chances to visit my alma mater, I should say, after I graduated more often. So uh, I really thank Merwari sir and Shoma ma'am for giving this opportunity and creating this platform which is a very good platform for everybody. Not only just us for sharing their experience, but for the students and even some uh, academicians. Professors, lecturers who want to know more about these new fields. So we hope to listen more from different field of these people from different field on this under this banner. And thank you for giving this chance to all of us.
Thank you, Yash, for sharing your vast information about scaling up operations possible through in flow chemistry. And on behalf of all the organizers, we extend very sincere thanks to you. And you have been with me since the initiation of this program, and how difficulties we encountered, and ultimately we solved all those, and we could get a very good platform with very good speakers. And we will now come to the concluding session. And in this session, I would like to mention to our students as well as our faculty members, researchers who are part of this program, who have joined here, with the NEP in going to implement in our state. I think this is one good opening session given to the all the participants, so that you can think of many such courses, programs for the students in order to enhance their skills, to make them understand new technologies, to gain some insight into new field, so that their career will be brightened, and they will get good opportunities of employability and doing good research. So all the speakers, they have been part of this program, gave an excellent presentation. They have shared their very vast experience in their chosen field very elaborately. They have given enough information to all our participants. Though our UG students, it may be a bit difficult to follow up because it is a new field, upcoming field. So, but with involvement and putting some little efforts, you can definitely gain mastery over this and do some good work in this field. And on behalf of all the organizers, actually, BVB College, KLE Tech University people wanted to involve very actively and take some responsibility, but they are having their NAC peer team visit from 7th, and all those faculty members are very busy. When I contacted Professor Amin Bami, he told me to discuss with Dr. Nagaraj Shetty, and whatever issues are there, you just share with him and you go ahead. And with that confidence, he asked us to go ahead, and we conducted this program today. And on behalf of Dandeli principal, management, IQAC, and all the faculty members of Dandeli Bangunagar Degree College, we thank all the speakers who have taken part in this webinar and shared their knowledge. And also, we thank all the participants who have been actively participated. Very good number of registrations were there, and our team will share the participation certificate within a couple of days with all the participants. And we take this opportunity to thank Mr. Abhishek Jakarnavar, who has been with us to make this live streaming platform, which went on more than 3 hours hassle-free because of his technical expertise. Mr. Abhishek, he guided us to create this live streaming platform, who happens to be the batchmate of my son. I got hold of him, and he has got some good expertise in making this live streaming platforms. He helped us, and he has guided us in creating this platform, and we are really thankful to Abhishek from Bright B Belgaum. And also, I thank all the faculty members, the participants who have joined in this webinar. Hope this has given some good insight, good thought for thinking in the days to come for the betterment of the students in the academic pursuit and in the improvement of our academic curriculum in the days to come. Overall, it was a very nice webinar with full of knowledge. I thank each and everyone who has helped me in conducting this webinar under the banner of the Dandeli Education Society's BN Degree College, the KLE Society's School of Advanced Sciences, BVPK Campus Hubli, and Consortium for Academic and Research Solutions, CFAR Solutions. So all these team has come together and conducted this webinar, and we will conclude here. And thank you each and everyone. And thank you very much. Okay, we will have the concluding of this webinar. Thank you. Abhishek?
Yes, sir. I'm concluding the session. I'm stopping the stream.
Abhishek, we also express our very great thanks to you also for creating this platform, and it went on hassle-free for all these more than 3 hours. And thanks to you, Abhishek.
Thank you. Thank you very much for the opportunity, sir.
Thank you. Thank you.